Very good afternoon, Shivram sir. This is Bhimal.
Very good afternoon. Are you able to hear me?
Yes, sir. I'm very
Okay.
excited.
Good, thank you. How are you?
I'm fine, sir.
Actually, I was, we were all beginning to travel a little bit, and now again the scare has come, So, you know, so anyway, once more the scare.
So I hope, sir, this time it will not true, sir.
Mr. Kamath, we can
We were
get.
supposed to have.
Yeah. Are we ready?
Yes, sir.
Okay. It's 4 o'clock, and good evening to all the participants at this webinar. My name is Ashok Kamath, and I'm the secretary of the IIT Alumni Center in Bengaluru. And we are co-hosting this with the ICPE this evening. So good evening to all those who are in India, and I know that there are a few from overseas. So some of them in the US might be very early in the morning. So very early good morning, and I hope you had your first cup of coffee. This is an important webinar in many different ways, and I'd like to just share a few things that came across very recently. Amazon in India is a company that makes 400 million shipments a year, and every shipment they have 130 rupees is the cost of their shipment, which is about $70 million in packaging alone. And out of the $70 million, 50% are plastics. And this is, we are talking one company. And if you add, other e-commerce sites like Flipkart, Snapdeal, even Starbucks, Zomato, and Swiggy, which we have now, in this pandemic times, we've become so used to getting food and drink delivered home in extensive packaging made out of plastics. You start to worry about, whether they are biodegradable, whether they are compostable, whether they are recyclable, and whether they are planet friendly. So in the context of all that, I think the work of ICPE becomes paramount, and it is our pleasure to co-host this webinar with them. The IITACB was formed for activities like this, where we want to bring in the power of science and technology to industry, and link industry and the IITs together. But more than that, I think webinars bring the messages out of saying, please listen to science and technology, because they can find a way out of our problems to the larger audience around the world. With this, I wish this webinar great success. I'm sure the recording of this will be watched by more than the people who are here today. We've had very good response, I'm told. But I think the larger thing will be that when this thing goes up on YouTube, more and more people will be able to view it and benefit from it. And from that perspective, I think it would be a job that's worthy of doing. With that, I hand over to Professor Ghosh to take this forward. Thank you very much.
Should I go ahead?
Thank you. Yes.
Okay. On behalf of Indian Center for Plastics in the Environment, I welcome one and all at this today's virtual conference on biodegradable compostable plastics. I welcome the distinguished and eminent experts to share their views on the most important, still often misunderstood subject in today's society at large. I welcome Padma Shri Dr. Swaminathan Shivram, distinguished Professor Ramani Narayan, Dr. Sundar Balakrishnan, Dr. Bhimal Khatir, Dr. Sunil Dhamania, Dr. Brajesh Dubey, and Sri Jivraj Pillai, who have agreed to speak in today's event and in the panel discussion. I welcome all the distinguished guests who have joined today's event and to know more about from the distinguished guests. I now welcome Sri S. Kire, Honorary Secretary of ICPE, to give the introduction to ICPE, and then to Professor A.K. Ghosh of IIT Delhi to introduce all the speakers and conduct the session 1 of this event. And over to you, Mr. A. Mr. A.
Mr. Ray, Mr. Ray, you have to unmute. Mr. Ray.
Muted. Is it okay now? Am I audible?
Yes,
Yeah.
yes.
Yes.
I'm facing a couple of technical glitch as well, looks like. So, Mr. Bandhavada, thank you very much. And good morning, good afternoon, and good evening to all our speakers and attendees, depending on where you are located now. My apologies for the inability to join this conference with the video option. Hope I am audible now. It's a privilege for ICPE in partnering this conference on biodegradable compostable plastics with PPA, Polymer Processing Academy, and IIT Alumni Center, Bangalore. Indian Center for Plastics in the Environment is a not-for-profit and non-partisan organization. It is supported by the industry, and its members are drawn from academia, NGO, and industry. The center was established in 1999 to give you a brief background of ICP's formation. It was on the recommendation of the task force constituted by the then Ministry of Environment and Forest, Government of India. Now it's Ministry of Environment, Forest, and Climate Change. Our activities include creating awareness about plastics and its relationship and connectedness with the environment. In pursuit of this, the center conducts awareness program for industry, for students, and for other stakeholders on responsible use of plastics and management of waste. We also sponsor technical studies and projects in related areas. The center had done pioneering work. I'm really proud of sharing this information in this forum on use of plastics in construction of bituminous road with CRRI and IRC, Indian Road Congress, co-processing of plastic waste in cement kilns in association with SEC Cement, and also did set up a demo pyrolysis plant way back in early this century for conversion of plastic waste into fuel. These are just a few to name the activities that we undertake. ICP also works and supports non-government organizations working in the field of plastic waste management and does conduct various events that actually goes towards sensitizing the future generation on responsible use and management of plastic waste. Today's seminar, as Mr. Kamath was mentioning, the sustainability issue has become a cornerstone of development during this century. At the dawn of this century, it has become a cornerstone for development. In this context, biodegradability has emerged as a major field of study to address challenges of plastic pollution. As usual, being an emerging field, there are different views and perceptions about biodegradability of plastics. Some of these are probably myths, but many of them are based on our current understanding of science, as Professor Kamath mentioned about. ICP is making an attempt in this conference to declutter the narrative and offer an informed view on this from different speakers coming from different segments who are knowledgeable and authorities in this field. I believe it would benefit all the stakeholders and help navigate the future discourse on the subject. My thanks once again to our co-partner, PPA, as well as IITB, IIT Alumni Center at Bangalore. Thank you, and I would request Professor Ghosh to take over and conduct this first session. Over to you, Professor Ghosh.
Thank you, Mr. Ray. We are for a very exciting session today with a very important topics, that is the biodegradable and compostable plastics. Because these materials, kind of alternate materials, are taking the very front stage nowadays, with a lot of emphasis on these areas, and biodegradable, compostable, and bio-based plastics are increasingly promoted as a solution to some of the plastic waste management challenges. More and more, all our consumer products, that's what we mentioned today by Mr. Kamath also, as a packaging, bags, single-use products, are being just getting labeled as compostable, biodegradable, etc., etc. But what exactly do these terms mean exactly? Where do we stand with this? To what extent can biodegradable, compostable plastics help solve the sustainability challenge that is posed by plastics? Hope they do not create a new one also. Keeping this in view, and also there is a need for standards in terms of these biodegradable materials, which has to be evolved, such as the condition of biodegradability, time for biodegradation, and the several alternatives in this regard may have to be researched in Indian context. Keeping this in view, today's session, I think, is very pertinent, very important, and without spending much time, I would like to begin with this session. We have a number of speakers in this session, 5 speakers. And I would like to begin with our first session, which will be the inaugural talk by Dr. Swaminathan Shivram. It's our honor to invite Dr. S. Shivram, who always been a very inspiring scientific personality for me personally. And Padma Shri, Dr. S. Shivram is a polymer chemist by profession and a mentor, as well as a science administration of distinction. He is a former director of CSIR National Chemical Laboratory, Pune. He was Shanti Sharup Bhatnagar Fellow of CSIR, J.C. Bose Fellow of Department of Science and Technology, and currently he is an honorary professor emeritus and INSA emeritus scientist at the IISER, Pune. Dr. Shivram is a highly decorated scientist with numerous awards and honors to his credit. He was conferred Padma Shri by the President of India in 2006. He is a recipient of the gold medal of the Chemical Research Society of India for his lifetime achievement in chemistry in 2019, and the International Award for Distinguished Contribution to Polymer Science is awarded by the Society of Polymer Science, Japan in 2017. He is elected fellow of all the learned academies of science and engineering in India, as well as the World Academy of Sciences, Trieste, Italy. He is a technical consultant to several reputed Indian companies and serves as the board of directors of many leading Indian companies dealing with chemicals and materials. Dr. Shivram's research interests concerns polymer synthesis, surface chemistry of polymers, porous polymers for energy-related applications, biodegradable polymers, today's subject, organic, inorganic hybrids, nanocomposites, and structure property relationship in polymers. These apart, he is deeply interested in subjects such as sustainability issues, sustainability, energy, technology, and policies, history of science, as well as understanding the interplay of science, technology, and public policies. And I am fortunate to be in a couple of lectures which I could be present and hearing directly from Dr. Shivram. He has authored close to 250 papers in peer-reviewed journals, edited 2 books, authored 1 book. He is cited as an inventor in 51 issued US and European patents, as well as 52 Indian patents. And he has supervised more than 40 doctoral students and mentored over 15 postdoctoral fellows in his research career spanning 50 years. So also I have to mention it's a remarkable year because Dr. Shivram has turned 75 this year, and this is an opportunity I thought I'll not miss to mention. And I will really pray that you may be blessed with good health, happiness, and we like to have many more years of your wisdom that we can get from you. Always, always, as always. Welcome, Dr. Shivram.
Can you hear me?
Now it's better, I think.
Are you able to hear me?
Now we have still some sound problem, Dr. Shivram.
There's some problem still? Okay. Can you hear me now? I was able to hear you. Can you hear me?
We cannot hear you properly, Dr. Shivram. Still, it is not clear.
Okay. Now, do I have the screen sharing? Can I share the screen? Do you have
No,
permission for screen sharing?
We can mute Professor ourselves, then maybe it is better if we do that, if we mute ourselves.
Yeah, please mute yourself. I can hear you, but I just want to know whether you can hear me. Can I?
yeah, now it's better. Now it's better.
Okay, because okay, all right. Now listen, I need to share the screen. So is somebody has to give me a permission, Mr.
No, sir, you can share
Bandap?
the screen.
Okay, because I have to share my screen. I'm just because I'm just a minute.
There's a green button at the tray bottom.
Yeah, I know. I'm just
Yes.
checking it out once. Just hold on for a minute and
Sure.
let me open my screen. Okay, now just a minute. Give me a minute, okay?
Should you please guide him?
Just a minute. I'm trying to share my screen, but it is not, my window is not opening.
Sir, you can open your slides and then share
Yeah.
screen and
Yeah,
share the
I
entire
have
screen.
opened my slide. Okay. But I have to see it on the screen, right?
Now you can press
Okay,
share screen.
now it comes. Now, can you see it now?
Yes, sir.
Can you see?
Yes.
Okay, now I'm going to go to presentation mode. Let me know whether you can see my presentation mode, okay? Can you see it now?
Yes, we can, sir.
Okay, now I'm going to move the slide. Just let me know whether my slide is moving, okay? Can you see this? Can you see this?
Can you go forward a little? Next slide.
Yeah, now can you see?
No, sir.
No, it's not moving.
Okay, so what I'm going to do, there is a trick for that. Okay, now see, now it's moving.
Not yet.
Sir, kindly go to the slide modes.
You have to go to the slideshow mode.
Yeah, I've gone to the slide mode, but now see, it will show, it will probably, you can see it in this position, but I'm trying to take it to the, see now, is it moving? No, no, right? Is it moving?
No.
No.
Okay, okay, I'm going to leave it at the earlier place and then start, because this, I do have this problem occasionally. I don't know why this problem comes. Now, can you see this? You can
Can
see
you
this
move?
slide?
You can see this one, but can,
Yeah,
now
yeah.
you can see, now
Now,
it's moving.
Okay, all right. I'm going to leave it here and not in the presentation mode. Okay, it's easier this way. Okay, all right. Okay. Thank you, Swapan. Thank you, Tushar Bandyopadhyaya. And of course, thank you very much, Anup, for that very kind introduction. I'm delighted to be here today. I don't know why I'm sharing this platform with Ramani. Ramani should have had this platform all by himself. You know, he can talk quite a bit on the subject, much more than maybe I can do. So thank you, all of you who are listening to me. I can't see any one of you in the audience right now, but I hope you can hear me and you can see my slides, okay? If you have any problem with audibility, at least just put on a chat message or just ask somebody to say, we can't hear you, okay? All right, thank you very much. So let me start, and I think this is a very interesting topic that has been chosen for today, and I think I'm looking forward to not only the presentation following mine, but also the panel discussion, because this is a topic that I think we need to debate quite a bit before we understand whether this is something of relevance to us in the future. So let me start my first slide, and I think this is a simple slide, and I think all of you are familiar with much of what I'm going to say. There's nothing that I'm going to say that many of you are not familiar with, but I'm trying to put in my own perspective. I think what we are really concerned with today, and if this entire searchlight on plastics is on today in this world, is basically because of the fact that the plastics that is used in packaging, and that is the one single source of angst and worry to both the governments, the citizens, and everyone. And I think the reason is because 40% is roughly of the plastics that we consume goes in predominantly packaging. Much of it is single-use packaging, and that's the problem. And that 40% is of roughly about 400 million tons, and that's a very large number. Now, if you just slice this 40% further, what you find is 88% comprises of three polymers: polyethylene, polypropylene, and PET. And therefore, I think if you want to kind of granulate our discussion, I think we should just talk about these three polymers. And I think we should look at this as our major problem area today. And if I just take out for a moment, and this is purely for an argument, that PET, let me say, I can probably handle it easily because PET is a class of polymer where chemical recycling could be a potentially useful solution. And therefore, if I just remove PET from this lot, then what you have is close to 78% is all we are dealing with polyethylene and polypropylene. And therefore, if there is a brickbat, if there is a blowback on the industry today, that blowback is predominantly on the polyolefin industry. And I think that's what I want to convey in this slide. And my own submission, and this is based on some studies that I have seen, I think we can do many end of the pipeline solution, but I think going forward, I think we require fundamental redesign for 50% of the packaging item. And that, I think, is the challenge that we have today. And actually, and that is by number and 30% by weight. I mean, we need to completely relook at the design in order to attain what I call a sustainability goal. Now, this is a challenge, and I don't think this is going to happen by simply shifting the burden of plastics from polyolefin to biodegradable materials. And I'm going to talk about that in a few minutes. So this is sum and substance of the problem that we face today. So if I say, what is the problem definition? The problem definition is essentially the 70 to 80% of polyolefins. And if you look at the Indian scene, in fact, the data show that in India, 50% of the plastics we make are actually going into consumer packaging in sector, and a large proportion of that proportion of the plastics we consume in India is single-use plastics in a very large way. Okay, when I say single use, I'm not making one use, but it is limited number of uses before we throw away that plastic. So that is the concern I think everyone has today. Well, this is why it's attracting attention. Okay, all over the world, every great journal you open today, plastics are on the cover page. I wish plastics were not on the cover page so much, because plastics are on the cover page of most of the journals. The reason is many: accumulating waste in the environment, leakages of end-use waste products in the air and water bodies, and most importantly, this has been kind of understated and understood in our larger community. A lot of plastics themselves are not unsafe, but a lot of additives that goes into plastics are unsafe. And these are small molecular weight additives. And over the period of time, when the plastics are there in water or in soil, there is a kind of a, leaching of these plastics additives. And in fact, today we know that much of these additives are entering the food chain of human beings. And this is actually a larger concern. In fact, this is a concern for the chemical industry in general, but this is also a specific concern for the polymer industry. And that's why I said we need to look at redesign of the products, not simply changing the product from one class of polymer to another class of polymer. It all depends upon what kind of additives you use, what kind of chemicals we use in plastics in order to make it more functional. Well, we can talk about this, and there are inadequate physical infrastructure for efficient handling of plastics waste. This is not only in India, around the world. And persistence in the environment, especially with long-term ecological effects. And today people are not so much bothered about the litter issue per se. The litter issue is one part of the problem, but I think people are bothered about what is the long-term ecological impact of a material like this persisting in the environment for years and years. And that is a question that is currently being asked, and much more answers are coming today. And that's one of the reasons why there is so much of discussion in the literature about these things. Well, the Indian packaging industry is at the cusp of a major change, and I think there are great experts here in this audience. It will be amiss of me to claim too much information, but India's plastics packaging consumption is about 12 to 15 kilograms per person. But if you go to a place like Delhi or Goa, it is already exceeding 50 kilogram per person. You can see here the consuming class, where they are located in urban areas, in tourist centers, where lots of people congregate, and that's where lots of plastics gets generated, waste gets generated. And they're all packaging waste. Unfortunately, and this I've been saying in many forums, 95% of the economic value of a packaging material is lost after one use. If not one use, maybe 2 or 3 or 4 uses. And this is a great concern. This is a growing market because we have a consuming class which is now migrating into packaged products. And you go to our supermarkets, you go to our malls, you will see what kind of packaged products are being sold in this country to consumers. It's a huge market, and I think it is growing at a compounded annual growth rate of 18% as far as I can see. At the same time, we are confronted with poor end-use plastics waste management systems, segregation, collection, infrastructure, disposal method. Everything is not so great in this country. And we have to keep asking our question, if 1.3 billion people start consuming 30 kilogram per person by 2030, do we have the resources to handle this kind of a problem? And I think this is a fundamental issue that we have to ask. Okay, if not by 2030, by 2040, do we have the ability to handle this kind of a problem if 1.3 or 1 billion people, you know, start consuming this material? So what I want to now say is that I think there's a great book written, and I'm sure many of you have read this book in 2018. It's called The Waste of a Nation. And I think what you must, I don't want to get into the details of this book, but I think I want to just paraphrase one sentence that is a very powerful sentence written in this book. Never in history have so many people had so much to throw away and so little space to throw it as the people of India in the second decade of the 21st century. And this is actually the big problem that we face. Okay. I mean, and that's the issue I think people are trying to address by a variety of solutions. And I think one of the solutions is to look for sustainability in our packaging material. But you know, sustainability is simpler said than done. It's easy to talk about sustainability than practice sustainability. It's a very difficult choice. And we don't know sometimes what choice we make is the right choice or not. And I think that's the situation we are in today with respect to biodegradable and compostable plastic. We can talk about it as a sustainable material. We can write papers in journals. The question basically is, are they truly sustainable? Are there unintended consequences that we need to worry about of even such a material? And I think the real danger in sustainability, because it's a complex problem, the real danger is when we simplify it. And I think that's the problem. Like Mencken said some time ago, for every complex question, there's a simple answer, and the simple answer is invariably wrong. And that applies to sustainability 100%. Well, lots of solutions we have today, and I think I don't want to discuss these solutions. I just put in blue the solution that we are talking about this afternoon, and that is biodegradable compostable plastics is one of the many solutions that we have to reduce this menace of what we call waste plastics packaging, which is predominantly polyolefins. Well, incineration and landfills. Landfill has been the practiced method predominantly, even in India. A large amount of these things end up in a landfill or incineration, and both of them, from a classical sustainability point of view, are truly unsustainable. And therefore, we have to look at a scenario where we will not landfill or we will not incinerate a plastic, because this is counterproductive to the global sustainability goals. And therefore, we have to go towards a system where we do not incinerate or we do not landfill. And that's a challenge to plastics today. Okay, I will not get into the discussion of these strategies, but that's for another day we can talk about. Well, there is today an utopian vision of a circular bioeconomy. And I want to call it utopian because it's truly utopian. Elegant in concept, but complex to implement. And this utopian vision is that people will say, and especially the professors like us will say, oh, there is no problem. We can take any renewable material. We can convert that into starch and cellulose. We can ferment them into products, convert them into polymers, and use them, compost them, and then let the compost regenerate the soil, and then we get back the renewable material. Looks very nice, especially if people are talking about circular economy, this looks very appealing. All I say is it's very appealing on a piece of paper or on a slide, but just think about the cost of doing this, and then you will realize that there are extraordinarily problems of implementation in this kind of a circular bioeconomy. Well, it's nice, but I think it is ideal. And we never reach ideality. And that's what the laws of thermodynamics tells me, that you never reach ideality. And this, I call it an utopian vision. If somebody wants to disagree with me, I'm open for a discussion. Well, why biodegradable compostable plastics? Because we do recognize that some plastics are difficult to recycle. I give you examples. Incineration, I already told you, a landfill is an unsustainable way of plastics waste management. And even if you can say potentially mechanical recycling, there is a limit to which you can mechanically recycle any plastic. At some point of time, this has to find a grave. You need an end of the life solution, and that's the problem. And in spite of our best intentions, if you have all the best systems in place anywhere in the world, we still have plastics will leak into the environment. And that's also a concern that people have today. And this has been discussed in many written articles. I don't want to get into the detail. And these are the issues that are currently bothering people around the world. Well, when it comes to biodegradable plastics, unfortunately, this has been around us for the last 20 years, and we have still not reached 1,000,000 tons. That's a pity. Okay. So the question is, if all this is so dandy, why are we not producing more of them? Okay. And that's a question you can ask. In fact, you can go and read this paper that I have given here. The reason is basically because, they don't meet the property requirements, of most of our currently used polyolefins, and that's the problem. So therefore, you can't say that we can replace polyolefins with biodegradable plastics. It's unlikely that it can ever do. Okay. And the problem is that all biodegradable plastics require a cleavable, a degradable bond. And this degradable bond is normally an ester bond and an amide bond. And without an ester and amide bond, you can't make a degradable or a biodegradable polymer. And if you introduce these ester or amide bonds in the system, especially in the aliphatic systems of esters and amides, then you destroy certain properties, and that's a reality. In fact, I show here in this slide that, when you look for a barrier packaging or a great packaging material, you don't want water permeability, you don't want oxygen permeability, you don't want microbes to attack them, you don't want carbon dioxide permeability, you don't want UV light degradation. That's what you will seek in functionality. And that's what polyolefin gives you. But then when you want to biodegrade a polymer, I need water permeability, I need oxygen permeability, I need microbial, ability of the plastics to kind of, get a foothold, microbes to get a foothold on the plastics. I need nutrients, I need UV light. Unfortunately, these are two contradictory properties. How do you build such two contradictory functionalities in one material? And this is a challenge. So when somebody comes and tells me that I can create a packaging material with biodegradable plastics, I tell them, please tell me, how are you going to build these competing functionalities in one material? That is, one material must have the desired functionality for use, and after you throw it away, it should have all the undesired functionalities. I mean, how do you do that? And that's a challenge, and we don't have an answer to this question scientifically or technologically, and therefore this is why it is bothering us today. Well, and somebody already said it's an awfully misused term, and I will leave it to Ramani to debate this and discuss this more. I don't want to spend time on this. All I want to say is we still do not have a plastics material which has the compostability properties equivalent to paper or kitchen waste. So that's the benchmark. Okay, can I compost like a paper, or can I compost like my kitchen waste, vegetable waste, fruits waste, meat waste? Can I compost it like that? There is no plastics that we can do this, and that's a problem. Therefore, compostability requires new infrastructure, and the new infrastructure, we are already struggling with existing infrastructure to handle the plastic waste, and nobody is now creating new infrastructure to handle another class of plastics. And that's a challenge that we have today. Well, you go to Delhi airport, I'm sure many of you travel through Delhi airport, you will see this in the vending machine. And this is from Pepsi. Okay, it says, taste that you love, eco-friendly packs, it's in lace. I understand this is made of polylactic acid, but you just flip this envelope or this packet, and what is written there is compostable in 12 weeks under industrial composting condition. That's what is written at the back in fine print. All right. Now, what does the consumer see this? Okay, you go and buy this, lace. You consume this lace, and where do you throw? You throw it in the garbage can. Does it go to your composting environment? No, it goes directly into a landfill. Okay, or for that matter, somewhere somebody will pick it up and try to recycle this maybe. Okay, there'll be a disaster. So the question basically is that by putting these kinds of products in the market without creating the associated ecosystem and infrastructure, we're actually doing a disservice to the community. Because what people now feel, and ordinary citizens feel, oh, this is eco-friendly, I can throw it like a paper in the dustbin. Okay, no, you can't throw this like a paper in a dustbin. Okay, so that's the problem. So by creating this labeling, we are probably doing a greater disservice to our community than maybe even a plastics packaging. It's nice, it's not eco-friendly, but at least I know how to handle it. It's a polyolefin or a polypropylene packaging. But this is a problem where I don't even know how to handle this. Now, where will I take this packaging material? To which composting environment I should take this, who will take it there, and where will it get composted? Nobody knows. So I'm wondering whether these kinds of solutions are what we now call in our parlance greenwashing. Okay, I think you know that our industry, especially the plastic industry and the consumer packaging industry, is doing a lot of greenwashing and trying to mislead the public. And this is, I think, a classic example of misleading the public. This packaging is available in the vending machine at the Indira Gandhi Airport in Delhi. Any of you passing through it can go and pick it up and see what's written on the backside of it. Well, there are lots of barriers to market entry today. Okay, scale and cost. 1 million tons compared to 200 million tons or 220 million tons of packaging plastics today. Performance still not satisfactory for intended applications. It requires, as I said, specially maintained conditions for biodegradation and composting. We don't have any labeling at all today. All these things are being labeled as number 7, which I find it ridiculous. 7 is others. Now, I think we should develop a labeling for compostable plastics. I think they have done so in America. They are doing so in Europe. I understand from what I read. I think Ramani can throw some light on this. But I think in India, we have no labeling. Everything is labeled as 7. Poor certification and testing infrastructure. Nobody tests these things rigorously. Of course, how to segregate a biodegradable plastics and where to take it. Nobody is telling me that. Okay. Regulators, I can tell you, are not comfortable introducing another class of material in the waste stream without appropriate infrastructure to handle them. And as you know, Australia has banned biodegradable plastics in the last 6 months. Because this is precisely the reason, because regulators say we are already tearing our hair what to do with existing material, and you bring another material and throw it into the same waste, and then you are asking us to create a new infrastructure for it. And they say, why should we do this? And of course, poor consumer awareness. And we don't know if I get a PLA. For example, you go to Starbucks in Pune, the coffee cup comes with a PLA lid. Okay, all right. Right next to my home, there's a Starbucks, and I go for a cup of coffee. The coffee cups come from a PLA lid. I asked the gentleman, where should I take this PLA lid and throw it? He says, I don't know. Throw it in the garbage can. Okay, that's the understanding we have as a common man. Okay, I mean, I asked the Starbucks girl, where should I throw this cap? Okay, I can throw the cup. It's a paper cup. I can throw it in one bin. Do you have a separate bin for PLA? He says no. Okay, so that's the level of unpreparedness we have of ability to take biodegradable plastics in consumer packaging. Well, I don't say there is no applications for them. There are very unique applications, and I think we need to look for them. Maybe they make sense there. For example, mulch films, plant pots, ground covers, canal lining, which is currently all low density polyethylene, could potentially shift to biodegradable material because that's the right application for them. Extrusion coatings for paper cups and cartons, adhesives, inks, and other additives. I think we have to focus a lot more on additives based on bioresources. because ultimately, I told you one of the large problems in waste in plastics is due to additives. And if you can make safer additives, maybe we will take the first few steps in the journey towards sustainability. Of course, textiles and non-woven for biomedical applications, filaments for additive manufacturing. These are some of the areas where I think biodegradable materials could be used, but let's not think that this is going to take away close to 200 million tons of polyolefins that we are currently using in our packaging application around the world. Well, this I will not spend time, but this is data in public domain. It's published data. Please have a look at it. And biodegradable, ask yourself a question, what is the sustainability quotient of biodegradable plastics? And the answer is not black and white. I always say all sustainability questions can only give you a gray answer, okay? And there's a lot of judgment that you have to apply thereafter. And this is also a gray answer, because if I show this slide, my polyolefin people will jump with joy, because it shows polyolefin is far more sustainable than PLA, you know, but that's not the answer, but that's the messaging that people get, because they try to pick the message that suits them, and that's the problem with sustainability. You always try to pick the message that suits you, and you try to talk about it. But then all I want to tell you is that sustainability assessment is actually not a black and white exercise. It is an exercise in gray. And when you have an exercise in gray, you have to do a lot of thinking, which I think we are not prepared to do at this point of time. There is one crucial meta principle of sustainability. And what is a meta principle for sustainability? For a system to be sustainable, it must not demand more from nature than that can be supplied. This is a simple meta principle. A situation in which this principle is violated cannot be sustainable. For long, because it results in resource depletion, ecological degradation, and transgression of local, regional, and planetary boundaries. And that is a broad principle of sustainability. The reason is that this is the touchstone by which we must check every solution of ours. And the reason I show this is, we all say that just because a biodegradable polymer comes from a renewable resource, it is a sustainable or a green polymer. It's not true, okay? Because we never match resource availability with potential demand. Assuming for a minute it's not going to happen, that all our packaging shifts to biodegradable material, would we cause ecological damage? Yes, we will. We will cause excessive amount of ecological damage. Nature needs time to renew itself. Nature did not create all these products to help man. Nature created these products to help itself, heal itself, survive. Now we as human beings, with all our greediness, extract the resources of nature in quantities by which it cannot renew itself, then we will degrade the nature, okay? And economic cost and environmental cost of extracting the resource from nature is not trivial. Most often we never talk about this, okay? And please understand that there's energy required to extract anything from nature. And going forward, this energy must all come from carbon negative or neutral energy. We can't use fossil fuel again for this, because then we are defeating the whole purpose of sustainability. And most natural resources, we must respect them as community properties of indigenous people. They are not resources for industries to exploit, and they must be exploited ethically. And that's the challenge before industry and society. And always I say this to my students, recognize that natural resources are neither free nor cheap. Beware of the dangers of the tragedy of commons. And I think this is the most important lesson in sustainability. So I think I skipped this. The future is not so bright. We are going to be generating 700 million tons of plastics waste by 2050. This is globally. But you can always prorate it population wise. And for 1.5 billion people on India, you can see what will be these numbers roughly, okay? And plastics entering the aquatic system, irrespective of all the solutions that we're talking about, okay? All right, you do all the circular economy, all the recycling, all the heat energy recovery, implement everything, Still, the model shows that 50 million tons of plastics will leak into the environment. Okay, and that is an issue that, therefore, people who say we can handle this problem are underestimating the complexity of the problem. We cannot handle this problem. I think we must recognize it. We can mitigate, we can minimize, we can't solve this problem by this method. So that's another issue that we have to worry about. Well, I think we have we are at the we are at a place where we need the time to choose. It's a time to choose. Can we decouple plastics consumption from GDP growth? Historically, plastics consumption has grown linearly with GDP. Okay, but is it necessary? And this is a question that I think we have to ask. And I think if we don't decouple plastics consumption from GDP growth, I'm not very sure we have science and technology based solutions for the future. So I think there is something else we need to do beyond science and technology. Well, I think as you debate these things, please ponder these questions. What is the consequence of a biodegradable, compostable plastics ending up in a landfill? There are dire consequences. I will not speak about it. I don't have the time. How do processors see the promise of biodegradable plastics? Because biodegradable plastics are notoriously difficult to process, okay, compared to polyolefins. Can biodegradable polymers be mechanically or chemically recycled? You know, when you biodegrade a polymer, you are losing the resource. Would it not be interesting to recycle even bio resources from nature? Because even resources from nature, even though assuming that you're taking it from nature, you must reduce the use, and therefore recycling is important. Recycling is not important only for fossil fuel plastics. It's also important for biodegradable plastics. Maybe we should not let the biodegradable plastics biodegrade. Maybe these are the issues that we have to ask. And I'm also asking the questions, are biodegradable polymers simplifying or increasing the complexity of plastics waste management? I think this question also has to be addressed. Well, it is foolish to think that technology alone is sufficient to address this problem of converting what I call a limited resource. I call nature's resources as limited. Many people think nature's resource is unlimited. Nature's resource is as limited as any other resource. In fact, oil is a nature's resource. Okay, fossil fuel is a nature's resource. It is a limited resource to satisfy an unlimited demand of humanity. And Joseph Stiglitz, a well-known economist, made this very perceptive statement: development is about transforming the lives of the people, not just transforming economies. Now, it's a very perceptive statement. Think about this, and I think you will start understanding the meaning of this very simple statement. Well, this is my concluding slide by James Speth, a very well-known American environmental lawyer, a founder of an institution, it's a not-for-profit called World Resource Institute in Washington, D.C. And he said that I used to think that top sustainability and environmental problems were human-generated waste, biodiversity loss, ecosystem collapse, and climate change. I thought that with 30 years of good science, we could address these problems, but I was wrong. The top sustainability and environmental problems are selfishness, greed, and apathy. And to deal with those, we need a spiritual and cultural transformation. And we scientists do not know how to do this. So thank you very much. That's the end of my slide. And thanks for my patient listening. I don't know whether I have taken a little bit more time than was assigned to me. But anyway, it was a pleasure talking to you. Thank you very much.
Thank you, Dr. Shivram. You brought together really the key challenges that is in front of us, and also the conflicts that we are facing. I think many our following speakers will be dealing with many of these points, hopefully. So let us see. Being a kind of inaugural address, there may be some comments in the chat box, but we are not taking any questions at this point. I'll move on with the other speakers.
During discussions,
Prof, you are muted, Professor Ghosh.
No, I think there was some. Yeah, so we'll move on with other speakers now, and I'll say that request the speakers to keep a little bit on time so that we conclude the session and we can have discussion at the end. as our second speaker, we are delighted to have Professor Ramani Narayan, who is in this area of biodegradable and compostability, and who else can be and to be with us to give the first keynote lecture. And we are meeting in many occasions, Professor Ramani Narayan, and this is another occasion when we are together for such an important event. Professor Ramani Narayan was named MSU University Distinguished Professor in 2007, which is the Michigan State University, which is the highest honor that can be bestowed on a faculty member by the university. And it governs states of Michigan University Award for Commercialization of Excellence, Michigan Green Chemistry Governor's Award for Biofoams Technology in 2011, University Distinguished Faculty Award in 2006, and Withrow Distinguished Scholar Award 2005, Fulbright Distinguished Lectureship Chair in Science and Technology Management and Commercialization with the University of Lisbon. And also he had the DuPont's Packaging Award for Excellence in Innovation and Sustainability 2010 as a part of the Coca-Cola plant bottle team. He was elected Fellow of the US National Academy of Inventors in 2015, Fellow of ASTM and ASTM Award of Merit, the highest award given by the society to the individual member, first recipient of the William N. Findlay Award for significant contributions to the application of new technologies within the scope of ASTM Committee D20 on Plastics, and Award of Excellence from Award ASTM Committee. He is a scientific chair of the Biodegradable Product Institute, technical advisor to the WWF Bioplastic Feedstock Alliance, and convener and technical expert on ISO and ASTM standard committees. He is advisor to EU Certification Organization and USDA Bio-Preferred Program. He has 200 referred publications, 30 issued patents. He has graduated 19 PhD and 25 master students. He is a successful entrepreneur, having commercialized several bio-based and biodegradable product technologies. With this, we invite Professor Ramani Narayan to deliver his talk.
Thank
Professor
you. Yes, thank you. I'm going to start my screen share, and I will do what Professor Shivram was not able to do, hopefully, which is to go to full screen mode. Let's do that. And now you'll have to tell me that you can see it in full screen mode. Otherwise, I'll have to switch. Anoop,
not
can
yet.
you see full screen?
Not yet, but it is visible fully.
Okay.
You can go ahead.
All right. You can see the full screen, correct?
Almost. Not the full screen yet.
Oh, it's maybe okay. All right. I will start, and hopefully, if there is a problem, let me know, and we can talk about that. I should say that it is a delight and a pleasure to share the platform with Professor Shivram, because he invariably messes me up with questions which I have to answer, and he probably thinks that I will be able to do some answering, because in the course of interacting with him, we have done that. I would, just for Professor Shivram, I don't know if he remembers, the subject of biodegradable plastics was discussed when he was the director of the National Chemical Laboratory, 20 years ago, and we are still talking biodegradables. So let me begin by saying that in this talk, I want to focus on the science of biodegradability, and want to also clearly differentiate biodegradability and compostability. Right at the beginning, I do want to address a very important question which Professor Shivram has raised. In fact, I don't know if you remember, he's raised this much earlier, which is what triggered my search for a a viable answer to that. And I will end with that, but I'm going to begin with this. The reason we are talking about compostability is that it certainly is defining biodegradability in a defined conditions or defined boundary conditions. And I'm going to submit that compostable plastics is being done not for managing plastics. It's not like recycling, but I would remind that 50% plus of the municipal solid waste stream in any country in the world is comprised of biodegradable waste. It's food, it's paper, it is wood, and that 50% of waste goes to a landfill in a developed world, and in an emerging economy like India, it is an open dump. Or even if it's a landfill, it's not a well-managed landfill. And under the anaerobic biological conditions of a dump or a poorly managed or even a well-managed landfill, all those 50% plus of the biodegradable organic waste which we generate is converted to biogas, methane, which, as anybody in this field knows, has a 25x GWP impact. So compostable plastics is to enable the 50% plus of the organic waste from a dump or a landfill where it is poorly managed and generate methane to a managed system where we produce compost and the carbon, 70% of that volume reduction happens, you produce a stabilized compost, and the CO2 is generated instead of methane. So the plastics, which we are now saying should be made biodegradable, and I fully accept that the biodegradability, and we'll talk more about that later as to the value of it, but compostable plastics is an enabler technology to ensure that food, paper, organic waste, which has to get diverted to manage biodegradable systems. You can't burn it because there's 50% water. You can't just throw it on the ground because obviously that is going to be mismanaged. And therefore, when we do composting, we need to get a clean, well-managed system, and therefore plastics associated in that system needs to be fully biodegradable, like its counterparts, paper, wood, and plastic. So it's not that we're going to make compostable and create a whole different waste management infrastructure. I would submit that you need composting infrastructure to manage the 50% of organic waste generated, which is already causing problems. So climate change and reducing greenhouse gases right front and center. If you took all the organic waste generated anywhere in the world, especially in India, and said, I need to compost it, you'll immediately see an order of magnitude reduction in GHG emissions because you're not dumping it, you're not making it anaerobic. So that's where the differentiation of why the concept of compostable plastics came. It is an enabler. It's not a solution by itself. And that was one of the big questions which Professor Shivram raised, and rightly so. And I want to make sure that is clearly understood. Okay, so that's number one. Number two, it's very interesting that what I am going to say is almost parallels what Professor Shivram has already said, but in a little different way. And I'll go more deeper into the science. So clearly, he has already mentioned that you have 359 million metric tons of worldwide plastics production. And he rightly pointed out that 50% of that worldwide plastics productions are polyolefins. And I want to reiterate that. And I didn't talk with Professor Shivram before he gave the lecture. And I'm very pleased that we parallel our thoughts on the same way. So 50% is, as you can see here, polyethylene, polypropylene, polystyrene, PVC. right? That's 50%. This is, you can look up the Plastics Europe data set on this. And therefore, I'm going to go a step deeper than what, and I'm glad Professor Shivram left it to me because he knew I was going to talk about this, that we're talking about carbon-carbon backbone polymers. And plastics is not just carbon-carbon backbone polymers. Plastic is something which you heat, flows, it imposes a shape on it, and you make products. And that's the beauty of plastics. But if you look at the hydrocarbon plastics, that is, as I said, 50% of the total production. And if you look at packaging, which again, Professor Shivram alluded to, that's 50% of the world plastics production is in packaging. This is the non-durable, disposable packaging concept. We're not talking automotive, electrical, building and construction. And I want to point out to you what Professor Shivram said, that if you look at this packaging globules, which you see here, PET represents 7% of that. So take that away. That means 93% or 90% plus of all plastics, I'm sorry, let me correct that. 90% of plastics used in packaging is polyolefin carbon-carbon backbone polymers. So instead of talking about plastics and the problems in general terms, I would reiterate what Professor Shivram said, that the focus has to be on carbon-carbon backbone polymers because that represents 90% plus use in packaging, which is the single biggest problem we face in terms of end of life and other things. So that is perfect sync with what Professor Shivram said, and I want you to focus on that. Of course, PET has got an ester backbone linkage, which is carbon-carbon backbone, and we'll talk about that in a minute. All right. So with that, let me move to this. Some of the questions which Professor Shivram raised is already appeared into it. The National Academies of Sciences and Engineering just yesterday released a report, and it is focusing on the US, not anywhere else. It is called Reckoning with the US Role in Global Ocean Plastic Waste. It's a wonderful reading, and not because I was part of that committee member which wrote this report, but it raises a lot of questions. And it does bring up some of the points which Professor Shivram raised, which he would very much like to see, because these were the simple things. What is the interventions that is needed? And in that report, we talk exactly like that. It goes all the way from decoupling plastics from economy by reducing plastics production, by redesigning materials for use, by developing better waste management infrastructures. All these points which Professor Shivram raised in a little different context has been captured in detail in this report, and I want to bring it up to this group to look at it. It does have all the solution, not talks about solution, it's on a very high level, and it talks about the contribution of the US. And this report will tell you that this was sponsored by the US Congress. There's a legislation which is called Save Our Seas Act. It is a bipartisan legislation which was introduced in Congress. And there is now more plastics restrictions, regulations which are being considered. So this is kind of a roadmap in terms of asking the US to take a leadership role internally first, and then put it out there to say, how can we deal with plastic waste? Because it's not going away. And it's not an easy solution of just turning something biodegradable or recycling, neither of which by itself is going to solve the problem. It's going to require intervention across that entire supply value chain. Okay. So I come back to this carbon-carbon backbone polymers, which, as I said, is 50% of the 358 million tons and 90% plus of the packaging, the disposable, single-use, non-durable products. And I am going to submit to you that the first take-home message I have is here. This is ubiquitous, lightweight, persistent, and this is what is polluting the land and oceans because it is not biodegradable. Right? Forget whether you want to make it biodegradable or not. It is not biodegradable, period. Its half-life is 100 years plus. You can look that up, right? So you cannot let it leak into the environment because it's persistent accumulates. You cannot leak it into the oceans because that's what we are watching. That's where that whole report is coming in. And I want to start this sort of lecture in a focused way to say that therefore, if you're claiming that you can add additives or enzymes or microbes to a carbon-carbon backbone polymer and make it biodegradable, make it disappear, make it go away, that is a absolutely scientifically unsound, misleading claim. And I will point out to you very simple. The carbon-carbon bond is the strongest bond. It's got 386 kilocalories per mole of, just look at the thermodynamics and the basis of it. To break that carbon-carbon bond by pyrolysis, you need very high temperatures, 400 C plus, you need catalyst, and even then you get a mixture of products. How can you therefore add a 1% of an additive into this molecule and say that at room temperature, mind you, landfills, oceans, compost, they are at very low temperatures, that at 25 degrees C, by adding 1%, I can break it down to small molecules of 100, 200, 300. Because in order for that to biodegrade, and we'll talk more about it later, those molecules have to go inside the cell. So help, as scientists in this group, explain and educate that, forget the additives part, can you add an oxo or any other additive that is capable of breaking a carbon-carbon polyolefin molecule to 100 and 200? Because if you could do that at room temperature, you would solve the problem. That's one of the issues, right? We are not able to recover it. It is very persistent. It is being designed purposely to withstand high temperature, and it requires catalyst. So I want to point that out to you in terms of making polyolefins biodegradable should not be in the picture at all. It does not work. It will not work. Your thermodynamics tells you no. Everything else does that. And that's where I want to lead with. Okay. So let's get into the molecularity of this. So here you have a carbon-carbon backbone, right? Which is what we talked about. And there's your ester backbone. Both are not biodegradable in the time frames of what we're talking about. So one is a carbon-carbon, one is an ester backbone. And now we got all the IITs and IISc Bangalore, which is sponsoring this, and many other very well thought out scientists and engineers. Can we not make more ester backbone polymers in a redesign of polyolefins specifically for packaging? It doesn't have to be starch. It doesn't have to be PLA. Although I would now submit to you that ester linkages is possible in a variety of combinations by using standard polymer chemistry, right? A diol with a diacid gives you an ester. Aliphatic esters don't have all the performance properties, so you move to an aliphatic aromatic polyester, as is shown here. But now when you introduce this aromatic linkage, it makes it not biodegradable in a composting environment, in an environment which is where we want it to go into. So what do we do then? So this is what BASF did. And they came up with, let me hold this back. They came up with a polyester, which you can see here, which has a random copolyester containing sufficient aromatic ring structure and the rest is aliphatic. So it's a mixture of aromatic aliphatic diacids with a 1,4-butanediol combination. And this is exactly what is not the complete answer, but the answer to Professor Shivram's question. Can we make biodegradable polymers which will still have the performances needed? And the answer is yes, it can be possible. You have to work at it. And here is the example, that by reducing the aromatic content and then increasing the aliphatic and managing that aliphatic aromatic ratio, you can come up with a polyester molecule that has performance properties, that is in use commercially today, but is fully biodegradable and compostable at its end of life, right? And that is the kind of redesign that polymer scientists and engineers have to come up with as replacement for the 90% plus carbon-carbon backbone polymers in use today, because if this inadvertently leaks into the environment, it's not going to accumulate and be persistent in the environment. That I leave the audience and the participants here to think about. Now, of course, PLA is also an ester backbone polymer, as you can see. And of course, the PHAs, the microbial polyesters, are also ester backbone. So clearly, we as scientists and engineers can design and manufacture polymers for packaging and be a replacement for carbon-carbon backbone polymers, which is where I think there is a lot of value. And if you use carbon-carbon backbone polymers and it does leak into the environment, into the oceans, onto land, they are going to fragment. But that's where the whole origins of microplastics, nanoplastics come into play, and it accumulates and is persistent. So we cannot develop persistent, non-biodegradable polymer molecules that has the propensity, like used in food and other packaging related applications, to leak and persist in the environment. Okay, so that's kind of where I want to bring the biodegradability discussions to. But I do want to point out one more aspect, the concept of bio-based, which was raised in several earlier sort of, not a discussion, but was raised in this meeting itself. And I want to say that bio-based has simply got to do with where does these carbons originate from. In other words, what feedstock, carbon feedstock you're going to use to make your polymers. Does it originate from plant biomass or does it originate from petrofossil? It has nothing to do with whether it will biodegrade or will it be recyclable or compostable as an end of life. So at the beginning of life, where does that carbon originate from? And that is the concept of bio-based. So bio-based is simply a measure of the percent carbon, fraction carbon, originating from plant biomass as opposed to petrofossil feedstock. And it has nothing to do with end of life. We can argue about what is the value proposition of switching from a petrofossil feedstock to a plant biomass feedstock. And there can be many arguments made for or against it in terms of that area. So that's all I want to talk about bio-based, and emphasize strongly that just because something is bio-based doesn't automatically confer biodegradability or compostability. And by the same token, biodegradability and compostability design doesn't need to invoke a bio-based carbon feedstock. Okay, so I've given you sort of a background on the molecular levels. And of course, Professor Shivram also alluded to polyurethanes. This is a big, to me, still a big question. Can urethane linkages break down under the conditions of composting, or what would be its lifetime, estimated lifetime, if it leaks into the environment? And what are the leakage products of it? And certainly something which, as a group, looking into this area should and can investigate. Of course, cellulose is your classic paper, and it's essentially oxygenate molecules. So if nothing, you can simply see that oxygenate molecules have a better propensity for end of life through biodegradation and composting than a carbon-carbon backbone polymer molecule. Okay, so that takes me back to what biodegradability really means. And this is very important because this is where all the confusion has come in. It has continued for 20 years, but hopefully this can be discussed. All right. So as we said earlier, in order for microorganisms to utilize this carbon, it must be very small. And really, isn't this the question we are asking right up here? Can microorganisms in the disposal environment, whatever the environment is, composting, soil, anaerobic digester, can it assimilate, utilize that carbon as a food source? And the key phrase is right here: completely remove it from the environment in a short, measurable time. It will eventually do it. But will it do it in a time frame that is acceptable and in the environment in which it is? Unfortunately, most of the work which we see, and we'll leave this for a minute here, most of the work which we see is in terms of the breakdown. So the additives technology part comes here, or you can have linkages like we showed up here, PLA, we talked about this. So either you introduce weak linkages, oxygen for matter, urethane for an example, or have additives in here to a carbon-carbon backbone. And everybody focuses on this step. It is broken down. The molecular weight is small. Microbial growth is seen. That is not biodegradation. Yes, it is biodegradation in a purely technical sense, but it does not satisfy the condition of complete removal from the environment in a short measurable time frame. And I'm submitting to you that is the biggest issue in all the discussions on biodegradability, and therefore the word compostable was actually initiated, because to differentiate from the fact that all organic polymers, organic chemistry is the science of organic carbon-carbon molecules, does give you breakdown. But that is not sufficient condition for biodegradability. Only and only if you can demonstrate that microbes will utilize that carbon completely in a defined time frame and leave no other persistent residues, then and then only have you removed it from the environment. So you cannot and simply talk about hydrolytic and oxidative enzymatic breakdown into oligomers and fragments. You have to demonstrate that those fragments are truly completely utilized by microbes in a short time frame as defined by the environment. And that I would want to sort of make sure you have this as a take-home message, right? This is where the biggest problems are. I did, my students did, a Web of Science research and said, what are the terms out there? Wildcard search with biodegradability, and do they really go to methods used? In the time span of 20 years, there's about 46,000 articles published that have the word biodegradable in plastics or polymer in them. Almost all review articles there talk about biodegradability. Out of these, 5,000 articles talked about biodegradability in oceans, marine environment. 144 had CO2, but only 31 articles had this. All of these talked about breakdown, but never talked about complete mineralization or CO2 evolution, right? So here is where I want to leave you with, that One, microorganisms utilize carbon as food to extract chemical energy for their life processes. They do it by transporting carbon into their cells. This requires it to be very small. And it cannot be done by adding simply an additive to break that down. Under aerobic conditions, basic biology teaches us that microbes utilize carbon by oxidizing it to CO2 under aerobic conditions, and under anaerobic conditions, CO2 plus methane. And therefore, why does this happen? Let me put this one up. This is the biology. The biological oxidation releases 686 kilocalories per mole of energy. That is harnessed by the microbe for its life process. This is the ATP ADP cycle, similar to why we eat food, to generate energy for ourselves. Microbes don't do it to clean up the environment for you, right? Therefore, if you want to prove that the microbes are utilizing the carbon and therefore removing it from the environment, you have to demonstrate conversion of that carbon to CO2 or CO2 plus methane by using the carbon substrate as the sole carbon source with the microorganism. It's basic fundamentals. So that's where this concept comes from. And this is the basis of all the ISO, ASTM, EN standards. I keep hearing all the time, we don't have standards. In fact, I think Anup and others talked about development of standards. Standards are there. We're not using it, and we're not doing it the right way. So whether you're talking ASTM or ISO, whether you're talking what the matrix is, and here's what the test is, very simple. I have a microbial test matrix. It could be soil, it could be compost, it could be a wastewater treatment solution here. I feed the microbes in there my test carbon substrate. I give it no other carbon food. If the microorganisms is utilizing carbon, then I should see CO2 evolution. Therefore, a plot of percent carbon conversion to CO2 on the y-axis against time in days will tell you how much of the carbon is being utilized. And here is the second take-home message. You can't stop at 10% or 15% and then it plateaus out and then extrapolate and say, oh, it will go to 90 in so many days. The requirement of all ASTM, ISO, EN standards is that 90% plus of the test carbon has to be utilized by the microbes as measured by the evolved CO2, because that's the biochemistry of the process, right? So there can be no debates. This is a factoid which we must take and perform and measure against, okay?
Professor Ramani Narayan, you have to finish in 2-3 minutes because of that time constraint.
All right, got it. So this is the standard we have. And I believe that, I won't talk about this much, but I believe that I had requested, and you people, the audience can get this paper. The purpose of this is very simple. One, you cannot design a biodegradable compostable polymer just from the structural perspective, but you need to know the receiving biological environment. That's number one. So you cannot describe biodegradability without describing the receiving biological environment. Two, 90% plus carbon conversion is a necessary requirement because that's what will confirm removal from the environment. And composting is a managed end-of-life environment. All right, so that I want to leave you with. I want to just go then to, because of time, I will leave these cautionary things where we can discuss it up, but there's a lot of misleading claims on biodegradability by addition of additives, and we talked about that for a long time. And this has been prosecuted in the US courts, US FTC, various NGOs have all put this that such claims are disingenuous and misleading. So I'll leave you with that. You can see that later. Okay. We also heard about mealworms and caterpillars eating plastic, and therefore a solution to that. I would submit that, again, it has to be removed from the environment. The last slide I want to leave you with and is to talk, which was raised by Professor Shivram in terms of infrastructure and where does composting fit into it. And I want to point out that 50%, where I began, 50% of organic biodegradable waste today goes to landfills or dump. And that is methane generation, which is 25x the global warming potential. That these need to be diverted from landfills and dumps to managed facilities so that you can reduce the volume and provide a stable soil amendment product at the end of life, right? If this is developing, then, and here is the numbers for you, if you recover 1.84 million metric tons of organic waste, forget plastics, through composting, you will get a GHG emissions reduction of about 1.7, almost a 1-to-1 equivalent of GHG emissions reduction. Therefore, what I am saying is that verified, certified compostable packaging associated with food, with paper, has to be compostable so that food and organic biodegradable waste can be managed properly. That is the answer to why composting. So composting is not going to happen because of plastics. It's going to happen necessary to make other organic wastes completely biodegradable under a managed system. And that recycling thin films to recover from food and paper is not going to be technically and economically viable. And leakage will happen. And therefore, you need to do a test to establish and estimate the time this will be in the environment should it be leaked. Is it 5 years? Is it 10 years? And we are just writing a paper on how this is to be done, but it certainly cannot be based on a carbon-carbon backbone polymer that is persistent and continues to accumulate in the environment. So sorry about taking time, and I will leave it there.
Thank you, Professor Ramanathan. Sorry for the interruption but there was a time constraint. But so clearly bringing out the science behind it. You may stop sharing and we move on. Okay. Thank you. We move on to the next speaker, and I will again request our honorable speakers to maintain the time, and we'll have a lot more discussion in the panel discussion so that we can reflect on some of the questions which may be coming in the question box. Okay. Our next speaker is Dr. Sundar Balakrishnan. Dr. Sundar is presently director at Naturetech India Private Limited, which is a subsidiary of Northern Technologies USA. And in the present capacity, Dr. Sundar is responsible for commercializing and marketing within India and also for SAARC region, the technology platform in the area of bio-based and biodegradable plastic. Prior to joining, Dr. Sundar was with head at Harita NTI. I had a lot of interaction during that time. And he was dealing with mainly in the comprehensive solution on corrosion management. And he was responsible for technology, technical support, and new product development functions. Dr. Sundar received his doctoral degree in chemical engineering from Michigan State University in the area of reactive extrusion of biopolymers and composites. He received his bachelor's degree in chemical engineering from UTCT Mumbai. He has co-authored several US patent and international publications in the area of bioplastics, and is also a representative on biopolymers at International Standard Organization, as well as Bureau of Indian Standards. He served as a national consultant to UNIDO International Center for Advancements in Manufacturing Technology in the area of bio-based and biodegradable polymers. With that, we invite Dr. Sundar Balakrishnan to give his talk.
Thank you, Professor Ghosh. Can you hear me?
Yes, clear.
Okay, and can you see my slides as well?
Yes, we can.
Okay, so first of all, I want to take this opportunity to thank Tusharji and the entire ICPE team for giving this opportunity. I want to acknowledge authorship to Professor Narayan, who has been my mentor, and it's an honor to share the platform with Dr. Narayan and Padma Shri Dr. Shivram and other eminent scientists here. I'm going to talk about the market development status in India, and apparently this last few years, compostable plastics or bioplastics have actually seen a lot of momentum and a lot of interest from the Indian market. I'll skip through some of these common slides, but essentially plastics consumption in India, majority is from the area of packaging. And there are statistics which says that by 2047, as a country, we would need about 1,400 square kilometers of landfill space at the rate at which the municipal solid waste is being generated in our country. A little bit about what are bioplastics, and I know this has been spoken at length both by Professor Shivram and Dr. Narayan. So bioplastics are essentially classified into two categories: bio-based and compostable or biodegradable. Bio-based refers to the beginning of life or the origin of the carbon which is present in the material. Is the carbon coming from a renewable feedstock, or is the carbon coming from a petroleum feedstock? And compostability or biodegradability refers to an end of life which determines the fate of the product as it is disposed in a certain infrastructure. It could be composting, it could be soil, it could be anaerobic digestion. And these are sometimes very interchangeably used. But these are two concepts which have defined value propositions individually. Now, if you look at bio-based and how does that relate to sustainability, as Professor Shivram mentioned, petroleum and natural gas also has a certain natural origin, which is essentially petroleum comes from biomass and crops over millions of years, basically fossilized over millions of years. And plastics which are made from petroleum and natural gas, over a certain lifespan, once it's being disposed, when you incinerate it, it gives out carbon dioxide, which is again fixed into the same plants by photosynthesis in the presence of sunlight and oxygen. Now, the way in which carbon is compartmentalized here, as you can see, the timescales of fixing carbon is in millions of years, while the timescales of putting it out is in 1 to 10 years. And this is basically a kinetic effect of an imbalance in the timescales of fixing to putting it out. And essentially what the bioplastics industry brings is, if we are able to make products directly from biological feedstocks, then we can manage the timescales of fixing carbon to the timescales of putting out or liberating carbon. And as a result, we are able to maintain the carbon dioxide levels at a point where we don't allow it to increase beyond a certain limit. So bioplastics or using renewable carbon presents the key value proposition of being able to maintain the carbon dioxide levels in the greenhouse gas, which protects the environment, and thereby the problems related to climate change is not there. And bioplastics or bio-based materials essentially need not be biodegradable. And it is not that all biodegradable polymers have to necessitate from a bio-based feedstock. We have the Bioplastic Feedstock Alliance, which is leading companies like Coca-Cola, Ford, P&G, Unilever, who have joined with the World Wildlife Federation, and they are looking at responsible development of bio-based plastics. When we look at biodegradability, again, as Dr. Narayan mentioned, this is a very misused, highly abused word, and probably the most greenwashed word that we can look at. Usually biodegradability or a biodegradable plastic is construed as a solution to littering. And I know I've been asked this question by several people when we go and sell these materials, that can you just throw it on the road? And no, the answer is yes. It's not a solution for littering. It's not going to disintegrate and just magically break down, but has to be treated through a certain infrastructure. And in the case of composting, it's basically the municipal or the industrial composting sites. And typically, compostability is nothing but complete biodegradability or 100% carbon conversion within a specified time period of 180 days in an industrial composting environment. And we have standards associated with this. We have the US ASTM D6400, which is given by the Biodegradable Products Institute. We have the EN 13432, which is the OK Compost standard. We have an Australian standard, and in India we have the ISO 17088 standard, where the products are tested at the Central Institute of Plastics Engineering and Technology, CIPET, and there is a certification given by the Central Pollution Control Board, Ministry of Environment and Forests, for meeting these ISO 17088 standards. Typically, compostable plastics have value when it comes to food scrap diversion. And adding on to whatever Dr. Narayan spoke about, it's a great material where we require food waste diversion. And basically, composting infrastructures are set up to manage organic and food waste, and they are essentially not set up for making just compostable plastics. There is also data by the Central Pollution Control Board that many times we have been told that in India, we don't have composting facilities. Now, if we look at the solid waste management rules in the country, the municipalities are required to segregate the organic waste. And typically 50% of any waste stream which comes out is organic in nature. This is part of the solid waste management rules itself. And there is also statistics by the Central Pollution Control Board that only 10% of the composting infrastructure or facility in our country is actually utilized. So there is municipal composting facilities which are unutilized. And essentially, these were created not for compostable plastics, but for food and organic waste. And if you look at this slide, essentially what we are talking about is when we make products. So let's say we have these food scraps, which is then contaminated. And now this is becoming even more critical because of the QSR culture which has come about. And there is just so much of plastics which are used with food waste, whether it's a cutlery or a coated paper product or a compostable liner bag. These products are collected, taken to this composting facility, composted, and then made products back. It's a perfect fit into a circular economy model. And compostable plastics aid in this because there are challenges, especially with recycling of plastics, especially when it's contaminated with food. And the cost and the energy that would incur in recycling food contaminated plastics is a lot higher. A little bit about global standards, which I already spoke about. So we have the US, Europe, Japan, and then the ISO 17088 standard. Now in India, the plastics waste management rules, which was amended recently in August of 2021, speaks about two key areas. Of course, there are lots of points in this amendment, but I just picked up two of this related to plastics. So the first one is there is going to be prohibition on earbuds with plastic sticks, balloons, plastic fags from January 1st, 2022, and then single-use plastic, especially related to short lifespan products like plates, cups, glasses, cutlery, straws. And if you can see this, most of this relates to applications which are in food contact. These materials are prohibited from July 1st. And there is also a statement that compostable plastics are exempted from this. So there is a driver in the Indian market right now to look at compostable plastics as an alternate, especially in applications where there is a certain food contact and a possibility to divert it to a municipal composting infrastructure. Again, I would also like to state that compostable plastics is not a silver bullet for every plastic problem. And I believe that technologies like paper, you have products in the bagasse space which is coming in, you have areca based products which are in the market. So all these products will coexist, and obviously technology is not going to be the only solution. It's got to be covered with a certain infrastructure to manage and a back-end infrastructure to collect it and take it to the right infrastructures, which is going to be true for any material. It need not be just for the compostable plastic. I just want to share a few applications we are seeing in the Indian market. I mean, there are over 125 to 130 companies right now in India which are certified by the Central Pollution Control Board. The Indian Compostable Polymer Association, ICPA, has been active in creating knowledge and awareness about some of these challenges and also about how compostable plastics are used. And currently we see applications in the hospitality segment. We've seen applications in the industrial space like, bus covers or industrial packaging for, vacuum cleaners, some of these kinds of products. And coated paper products, as Professor Shivram also mentioned in his one of his concluding slides, coated paper products are definitely gaining a lot of market traction in India, especially products like coated paper cups, paper plates, basically, popcorn tubs, anything where the single use, where the lifespan of the material is very less. The other thing that's also driving the market in India is there is a huge processing industry in our country which is very accepting these materials because we don't require a huge infrastructure change to run compostable plastics. Typically, most compostable plastics produced in the country are run on existing infrastructures which are used for conventional plastics. Maybe with slight modifications, maybe you need some dehumidifying dryer setup or some small changes in the temperature profile of how you run the extrusion, but pretty much these infrastructures are very standard. So that kind of gives the processing industry another alternate, at least in certain applications. Again, I would like to reiterate, it's not a silver bullet. It's just in certain applications, there's absolute value in using this. This is more of some of the durable applications. And then definitely there's momentum into structures, into hybrid structures with paper. And again, barrier is a major concern because obviously compostable plastics do not have the necessary barrier properties which is there in conventional plastics. So compostable plastic by itself is not going to meet those requirements, and thereby creating hybrid structures, marrying it with products like paper or foil or metallized paper. These kind of products bring value in terms of both meeting a certain barrier requirement and also being giving a clear end of life. And paper chemistries are very exciting. What we are seeing in the market is paper as a product has certain advantages, and then compostable plastic has certain advantages. And when we marry these two products, it's almost like an alloy where you are bringing the best properties of paper and compostable plastic together to give a much value added product in the market. This was a case study we had done with one of the brands where this was purely on the bio-based value proposition. We had replaced a certain size bag with a compostable bio-based product, and we were able to reduce the total material carbon footprint by about 350 tons a year. And to translate it more into layman words, this was similar to emissions reduced by driving a car for about 138,000 kilometers, or saving about 1.5 lakh liters of petrol every year. So bioplastics also can provide these value propositions in terms of, carbon footprint reduction. This was a case study we had done with the Godrej team in Chennai, where we had been involved in the construction of a composting infrastructure in their facility. There were about 500 workers in that, and with this facility, we were able to manage all of their organic waste which was being generated, along with their garden waste, lawn and leaf waste, and these waste was collected in compostable bags and then treated and then subjected to composting. And we were able to generate get about 80% volume reduction with this, and the manure which was generated was actually applied back into the same gardens. So this is again to show how the actual compostable bags break down. Some of the biopolymers in the market, in terms of bio-based, we have polyethylenes, PETs, polyamides, polypropylenes, and then fully biodegradable materials. The key polymers are PLA, PHAs, PBS, PBAT, and these materials are all of them have a certain, I would say, functionality and a certain property. And there's a lot of work in terms of how do we create compatibilized blends of these polymers to meet a certain application. I mean, compostable materials or plastics have not exactly taken on or reached the technology realm that conventional plastics have. I mean, it's still a baby compared to conventional plastics. There's a lot of work that needs to happen, but it's exciting times, and definitely there's value in terms of kind of creating chemistries on these polymers to be able to meet certain end applications. A very quick, just a few slides about our company, and then I'll close. So Naturetech is part of Northern Technologies International Corporation, a publicly listed company in the US, headquartered in Minneapolis. We were founded in 1970. We have 20 JVs and 3 subsidiaries around the world. We have a global revenue of about $175 million, and we are a zero debt company. We have essentially 3 brands. We have a brand in the industrial packaging space called Zerust Xcore, which is corrosion management solutions for automotive and auto component industries. Zerust Oil and Gas, which is again corrosion management services in the oil and gas space for large petrochemical companies like Reliance or Petrobras in Brazil. And then Naturetech, which deals with bio-based and certified compostable plastics. The Naturetech portfolio is divided into 3 main product lines. We have a range for apparels. We do a lot of work in the textile space. We have products which are transit packaging bags for textiles, hangers, clips, tags. So any plastic accessory which is used in a textile, we have alternates for that in bioplastics. We are also in the zero waste solutions. We do liner bags, shopper bags, cutlery, gloves, straws. So again, anything that fits into a certain food waste diversion stream. And we also do compounds, which is bio-based compounds and formulations tailored for specific applications. This could be in the consumer packaging or in the agricultural space. We have a team in the US which is dedicated to product innovation, support, quality control. And we of course have a strategic collaboration with Michigan State in the Department on Advanced Bio-Based Materials. We have projects funded by National Science Foundation, US Department of Defense. In terms of our global capabilities, we have manufacturing in Asia, Europe, North America, and we have labs in the US, and we have technical centers in India and China as well. To conclude, I would say bio-based and biodegradable plastics are effective alternates in certain applications. Carbon footprint reduction and effective end of life are drivers for adoption. And there are applications in all industries ranging from textiles, leather, automotives, electronics, to name a few. And definitely these materials contribute to a greener supply chain. They are an alternate. Again, I just want to say that they are not the only alternate, but definitely in certain applications, they add value, and they're able, and we are able to really create a better circular economy with these materials. Thank you, and be happy to take any questions. Thank you.
Thank you, Dr. Sundar. And I think we will go for, because of the time, we'll go for the question answers session along with the panel discussion where there is a questions. Okay. I would now really like to invite Professor Bhimal Khatir. Bhimal Khatir is currently professor in the Department of Chemical Engineering. He is Dean of Research and Development. He is head of the Center of Sustainable Polymers at IIT Guwahati. He is also an honorary senior fellow at Kyoto Institute of Technology, Japan, and visiting professor at GIFU University, Japan. He is also honored as a chair professor in Numaligarh Refinery Limited and Hindustan Gums Company Limited. He received his PhD degree from Chemical Engineering IIT Bombay. His main research areas include sustainable polymer developments, its processing, structure property relationship, rheological aspects, structure, the polymer degradation, polymer-based nanomaterials, food packaging, clean and green energy technologies. He is a coordinator of 3 centers of excellence in IIT Delhi. He is dedicated in developing cost-effective, bio-based, biodegradable plastic products and its related technologies using various feedstock, including bio-derived plastics and biopolymers. He is a co-inventor of 29 granted or filed patents. He has published more than 130 peer-reviewed research papers in the reputed journals and more than 250 conference papers. He's been engaged with more than 15 projects in the areas of sustainable polymers and related technologies. With this, I invite Professor Bhimal Khatir to deliver his talk.
Yeah, thank you, sir. It is really a great honor for me to speak before such a august gathering, and especially before Professor Shivram sir and Professor Ramani Narayan. And the fact that, sir, frankly speaking, I'm agree with both of you. And that will be really giving a great confusion that what to speak. The fact that, so I thought that it better to speak what we are doing it. And certainly it's a really great day for us, all of us, that we learn from both the perspective. Absolutely right that this is a great, I mean, say really very good area of research. But at the same time, it's opened so many questions as well. Like when Honorable Shivram sir has mentioned that ecosystem need to be established before entering into any new domain, and that is going to be mostly on waste disposal management. If you're really going to talk in general, like country like us, the fact that would you like to educate first to each and every citizen that how to handle the conventional plastic or the bio-based or biodegradable or compostable plastic, and how to identify it, where to throw it, and are we going to recycle along with the conventional plastic? If it is, then how to do it, because both backbone structures are different and processabilities are different. So many challenges. Though we identify there are a possibility to come up with this new class of a material, if we really relate with the sustainability, certainly we will be going to have more some of the advantage, as the previous speaker has already mentioned. So today I'm going to talk about what IIT Guwahati is doing in this regard. So, sorry, slide, yeah. So I would like to first tell you that the IIT Guwahati is one of the first institute who have started as academic center on sustainable polymers, and we have started our PhD program on especially on sustainable polymers. And from the July 2022, it will be going to be a master's programs in the area of polymer science and technology. And I would like to acknowledge here Professor Ghosh and our honorable Professor Mishra with their mandate, with their mentorship since long, we could able to reach to this level. So thank you very much. So here, as it has already been mentioned, that at IIT Guwahati, since so many years, we are trying to establish a protocol, try to establish a SOP in order to develop a biodegradable plastic. As we understood that, there are certain advantage as well as the limitations are there. We understood about, if you consider about bio-based biodegradable plastic, we consider one is, if you're really going to talk about the bio-based plastic, it's going to be help us. It's a beginning of life. It's going to help towards the reducing a shorter, bringing a shorter carbon cycle. However, biodegradable polymers, which is going to give a end of life impact, and it will be good to remove a carbon from the environmental compartment. And this I learned from Professor Ramni Narayan, sir. Thank you very much. So here, as Sundar has already shown that if you are really going to see our kitty and find out which particular so-called bio-based biodegradable plastic is going to be having a good market share, and that we of course say that is polylactic acid. I would like to highlight here, there are certain, it's a very good material. As soon as it has previous speaker has mentioned, it is nice processability. It can go along with the conventional machining. So the fact that if you would really like to come forward with this, but this kind of a material, we really need not to disturb our downstream processing value chain. That is very, very important. And another way if we consider that it's going to have a huge manpower intensive industry. So that way this kind of a material is good. But frankly speaking, what are you going to replace? If you are really going to replace a water bottle, if you are going to replace a PET, as Professor Shivram has mentioned that water vapor and OTR, oxygen transmission rate, these are the challenging issues if you're really going to use this material for I mean to say stringent food packaging applications. Or if you're really going to use this particular material for a high service life, I mean to say, should we replace a backbone because the heat distortion temperature or heat stability temperature is around 70 degrees? We could able to increase by addition of the fillers. Then again, the migration issues come into picture. So the material is very good. Hello? Is it okay? Okay. So this particular material is very good. And the fact that, but we have a certain challenges. So we are working more or less in the development of these class of polymer, and especially as we understood that there are certain well-defined rules to use this material, to dispose of this material, but may or may not be useful in our ecosystem. So the fact that we have to, as it has been mentioned in the inaugural talk, we have to rethink from the beginning that what exactly we want, how we are going to disseminate the material, and how to bring those properties into the backbone of, I mean to say, in the polymer. So I'm just giving you a certain example. If you're really going to replace a PET with the PLA, we have to reduce oxygen transmission rate and by 10-fold, water vapor transmission rate by 2 to 3-fold. Values may be a bit here and there. We try to make various attempts. A lot has been done that, okay, you can increase the heat stability temperature with this material. Many additives has been added in order to tune the diffusibility coefficient of these diffusion molecule into the polymer. We have also done various aspects on this, adding different clays, and finally when we have done trial that we could not able to reduce the oxygen transmission rate at a first principle at that particular level. Because why I'm talking about this, because the question raised that there are a structure property relationship that is not matching with our requirement. So later on, then we realize if we really going to add, Professor Shivram has mentioned that additive manufacturing itself is a gray area. And if we really would like to enhance, if we are not changing the backbone of the polymer, then certainly we have to come up with a new additive so that we could able to match the structure property relationship. So here I would like to give an example. even sometime we, instead of, tuning the permeability, we can tune the, if you really would like to reduce the permeability, either we have to tune the diffusivity coefficient or we have to play with the solubility coefficient. So we realize, instead of tuning a diffusivity coefficient, if you will tune the solubility parameters, solubility coefficient, that we could able to reduce oxygen transmission rate and bringing it to close to the PET. So some kind of, we understood that if you will take this synthetic plastic and bringing with the bioplastic, the biopolymer, and that kind of a composite can lead to the properties what we really need. And these class of hydrophobic master batches can be used in order to bring it to this level without compromising the mechanical properties. However, some of these plastic, especially when we talk about the PLA, the glass transition temperature is significant. It's a higher, and we really need to reduce tune this particular parameter in order to have a more applicability. Frankly speaking, when we talk about the standards and how the standard has been made, as Professor Shivram has correctly mentioned, that one of the package it is written, it is 90% compostable, is going to be at 58 degrees centigrade. We understood that the industrial composting is really required for the process, but do we have that kind of infrastructure, or we are going to mix it with a regular plastic? That is going to be a chaos if you are going to recycle the materials. So the fact is that either we have to reduce the performance, the compost, accelerate the composting process and bring it to, and composting at a room temperature, the soil condition. I think that will be also one of the area where we have to look into it. So because most of the time, if you are really going to use these cutleries and packaging, and littering is a very big challenge for us. So we realize, frankly speaking, what exactly I want to tell you, if you would like to bring the bioplastic along with the biopolymer together, we have found that enhance the compostability significantly. So, and we could able to find out, we found out that it also compost it at even lower temperature and the soil condition. I'll show you here. Then the processability comes into the picture. How many times we could able to recycle this very well-known polymer? Like so we have found that certain additives, bio-based additives, can important role. We work on the nanocellulose or these cellulose, crystalline cellulose derivatives. These derivatives can help us if you're really going for the reactive extrusion process. And we could able to find, if you will see it here, that when we were processing with our facility, like 20 centimeter slit die was giving around 13 to 14 centimeter film at a winder. However, when we process with these particular additives, what we added into the polymer, we could able to end up with the more than 18 centimeter wider film onto the winder. However, the slit die was 20 centimeter. So we could able to improve the melt strength significantly and reduce the wastage of this class of a polymer. And the fact is that we could able to recycle this class of material. So we tried to recycle these materials, and we found that we could able to recycle this material three times. However, the tensile strength has been reduced, though it will be going 50 to 50 megapascals. But however, after recycling, we could able to get a tensile strength of around 30 to 35 megapascal, which is close to the LDPE strength. So I mean to say, possibly with the inferior, I mean to say here, I just wanted to focus, we could able to recycle this material for certain purpose, where when we talk about the circular economy, so bringing it from a one particular, the waste product could be used as a precursor for another steps. Those things we are also working here at IIT Guwahati. And a lot has been done. In fact, not only, so I just wanted to tell that it is not only the bioplastic, but also biopolymers will also play an important role. And that can be also exercised even though cellulose base is the transparent cellulose we are working on, that can be used for one of the alternative of the packaging. Another thing we are working, utilizing this class of polymer as I mean to say, as an industrial polymer, and where could able to, or we can use for a high temperature applications, especially automobile and other engineering applications. So we try to work on this development of this stereocomplex polylactic acid. Here, more important, a lot has been done in the stereocomplexation, but our approach is that to make it this stereocomplex polymer with the industrially viable technique. So we are using, it is a no solvent process. It is going to be a common extrusion process. However, that certain master batches are really going to give an impact to bring this, I mean to say, bringing this stereocomplexation into the in a very effective manner, especially for a high molecular weight polymers. So if you're really going to see it here, if I'm going to add the CMC, modified CMC, or the modified chitosan, you could able to see that in a normal case, if you are going to mix the lactic PLA and PDLA, and you would going to get both homo and stereocrystals. However, after addition of this small percentage of additive, you could able to get the only the stereocrystals. As the time is limited, I am just running short, bit fast, but I hope the message will be clear. So you can see, here we talk about the heat stability temperature for higher service life. You can see in our case, we could able to have reached to the heat stability temperature around 140 degrees centigrade in relation with the conventional polymer. So we could use this kind of material for a higher engineering application, higher temperature applications as well. So I would like to show you, here we have the monopolymer, I mean to say homopolymer. And you can see when I'm pouring a hot, the boiled water, what is the state? There is the problem with the material. However, when we are going with this stereocomplexation, you can see that these trays. So we have tuned, basically, you can see that it's quite improved in the performance. However, you know, in Indian scenario, we used to eat and drink beverages in basically at a higher temperature. So that way we could able to tune as it has been mentioned, we can tune either the backbone structure or the crystallites in order to get the better performance and better product. And more importantly, those technical intervention has to have with us, because how we can be more relying onto the other sources. So we are doing on these lines. Similarly, we started from the first principle. We do our polymerization. We have done it at small scale as well as the large scale. We also compare with the commercially available materials as well. So here you can see that these class of the bioresorbable implant and fixation devices can also be made. So you can see that these technology we have reached to into certain level where it can be taken by the industry from here. So these are some of the technologies. So similarly,
Bhimal, you may, if you can kindly come to the
okay. So
2-3 minutes.
We also tune the backbone structure in order to mimic the properties of the polymers, making a very flexible, elastomeric kind of a polymer to going to be the semi-rigid polymer. So very many interventions has been made in order to develop this class of a polymer and with the desired properties. So we demonstrate the activities what we are doing here at a center, and some of the activities has been acknowledged from the government. And here we are also working on utilizing a bamboo, and that is we are doing with the Numaligarh refinery. They are coming with a bamboo refinery, so we are working with them to taking a one block of as an intermediate from this particular refinery and converting into the bioplastics. So that particular interventions Our main focus is that to develop these class of material indigenously with us. There are certain limitations with these material. At least we have to have a strength and capabilities to demonstrate and to showcase with on this. So I mean to say we are not limited only for going to the commercial, I mean to say the plastics. We are very much working on the edible packaging, and we have come up with a very good solution, especially for the tomato, onion, potato, how to improve the shelf life by having bringing a biopolymers and increase in fact the shelf life of these materials. So trying to figure it out that whatever the resources available with us and how many, I mean to say the intervention can be satisfied, that what we are doing here at the center. As so the time is limited, so I would like to tell you, even though it is related, we talk about one particular model polymer, and one thing I would like to tell you, we have found that even the residue of these polymer, if we are going to add into the oil, especially like biodiesels and those, we have found that even the exhaust emission, the engine performance has improved significantly, and the fact that it will be a good additive, even though the residual polymer can be used as a good additive for even improving the exhaust gas emission characteristic of certain oils. So the details can be seen. We are also working on this, and we discuss a lot about the composting. We understand that it is going to be an industrial composting, but the fact that it may not be feasible, if you're really going to talk, I'm just skipping the slide, you can see that most of the time, if you're really going to see in the soil condition, these polymers are not following the line which has been written as standard. So are we going to define our own standard as per our need? That is also one of the questions. And if it is with our habits and the way what we are administrating these kind of polymers, that's very important. We are trying to develop the polymer, whether the same or the different class of a polymer, which can degrade, I mean to say compose at the soil conditions. We are very much into it, and we are working on it. Okay, so I will just stop myself that what IIT Guwahati is doing, and the fact that long way we have to go with these class of material. We understood there is not a single polymer compostable material is going to replace all this, but we really need to have a different class of material, whether for a flexible, semi-fixed flexible, as well as the rigid polymer. A lot need to be done in this particular area. But we have to start, we have to be self-reliant, and we have to be to deliver the indigenous technology. This is the basically need of the hour. Though there are certain bottlenecks, we have to address across. With this, thank you very much.
Thank you. Thank you, Bhimal. I think there will be a lot more interaction during the panel discussion. So we take you, all the interactive questions may be there. There will be a lot more discussion there. Okay. Thank you, Professor Bhimal. In this session, we'll finish with one more talk, and that is from Dr. Sunil Dhamania. I'm happy to see Sunil in the panel today because he is our student. He got his PhD degree from my own department in 2012 at IIT Delhi. He is currently Senior Research Scientist at Polymer R&D Reliance Industries Limited in Mumbai. He is associated with Reliance Industries for 9 years now, and his research interests are in polymer through renewable resources, biodegradable polymers, his blends and composites, and polyolefins. He has number of publications and 15 patent applications he has submitted. With this, let me invite Dr. Sunil Dhamania to present his talk.
Yeah, thank you, sir, for your introduction. And a very good evening to all the participants and the distinguished speakers. Let me upload my presentation.
Please stick to the time of 15 minutes, huh?
Yeah, sure, sir. Let me know if my slides are visible.
Yeah, it's visible. Go ahead.
So in this presentation and talk, I'm going to talk about the process industry status of the compostable plastics. Now, this is the standard slide of my company where it is stated that the statements, opinion, and predictions which is making in this talk is strictly related to the present and author. Reliance policies and Reliance itself is directly not related with us. And whole presentation and this talk is totally restricted to the knowledge sharing purpose only. Now, Reliance is continues to producing made in India, made for India, and made by Indian products, and it is aligned with the business with the national goals and priority for making the India self-reliant, strong, and prosperous, and by harnessing the power of the new technologies to fire its diverse growth engines. Reliance is having in this decade 3 mega growth engines, and the first of them is the Reliance Jio, and we are having more than 426 million subscribers, and this is the first operator outside the China to cross the 400 million subscribers in a single country market. Second, our growth engine is the Reliance Retails. We are having more than 150 million customers, and we are supplying diversified product portfolio of the groceries, fashion, lifestyles, and consumer electronics, and we are connected these through online services and more than 13,000 stores. And our third growth engine is the Reliance Oil to Chemical, and where we are providing the transportation fuel in one of the fastest growing energy markets and supplying the petrochemicals to diversified end-use industrial manufacturing, essential industries, and consumer goods using various kinds of polymers and polyesters. And now coming more about our O2C business, Jamnagar is our super site where we are having the largest and the most integrated O2C complex, and we are also having the world's largest ROGC and LIDP, LDP and MEG plants, and we are also having the largest single location paraxylene facility. And our other domestic sites are the Hazira, Dahej, Nagothane, and Vadodara. We are having the cracker integrated sites, and we are producing polyesters for different kinds of polymers, elastomers in the integrated downstream chains. And we are also having the ethane ports. We are virtual pipeline for import of the ethane from the surplus US market to RAL crackers. So we are having the feedstock security, flexibility, and which brings the reduction in the volatility in the business. Now, if we talk about the more on the our O2C business, we are having various segments in this O2C portfolio. We are the first is the fuels. We are having gasoline for the application of the transportation fuels, and then we are producing the various kinds of polymers like the polyolefins, like polyethylene, polypropylene, PVC, and which are having application in the construction, agriculture, automobiles, and the consumer goods. In another segments, we are having elastomers. We are producing PBR, SBR, butyl rubber, and which are having application in the tire and automobile industries. Our next section is in O2C business is the aromatics and the fiber intermediates. We are making purified terephthalic acid, EOE, and paraxylene, which are having applications in the polyesters and the textile industry. In particularly for the polyesters, we are making yarns, staple fibers, and PET, and which are application having in textiles, apparel industry, and beverages. So coming to the today's talk about the biodegradable polymer, or widely we can say the compostable plastics. So as we know that the global production is more than 400 million metric ton of plastics, and plastic is a wonderful material and so far the most useful material which is invented by the humans, because it is having the application in each sector like the health sector, clean energy in form of the wind turbines or the solar panels, safe food and commodity applications. But over the years, the plastic is having its inherent quality because it is inexpensive, disposable, and durable, and that is why over the years the increasing plastic pollution is also converted into the plastic waste, and because it is not getting degraded so easily, that is why we are facing the problem of the plastics. So there is a perception change from the plastic from a wonderful material to a problem, but it is mostly related with the consumer behavior and the mismanagement of the plastic which is produced so far. Now, if you look at the plastics point of view and which is creating the plastic pollution, the single-use plastics are the mainly responsible for that, and single-use plastics can be defined that the plastics which are designed for the immediate use, and these plastics are generally discarded the same year it is get produced. So, and if you look at the sector point of view, packaging industry is the largest contributor to the single-use plastic, that is around 36 to 40%, and then comes the textiles, building constructions, chemical electronics, and the consumer products. And we looked at what is the current scenario for these single-use plastics and how they are treated. So only the 14% plastic get recycled, and rest 40% go for the landfills, and only 14% get incinerated to generate the energy, and around 32% will get leakage into the environment. So roughly the 86% of the plastic get disposed and littered in the environment. For plastics as a plastic pollution is there, so there is a certain plastic waste management things are there, which currently is being in application. First is the incineration, where we can take simply plastic and burn it out to take it the energy. But burning of the plastic is also generating the harmful chemicals, and which are creating the problems like the various diseases like the cancer, neurological damages, endocrine disruptions, immune damage, asthma, and different others. And the second thing, second solution is the recycling. And recycling is a very powerful tool to use the plastic again and again, because plastic is easier to recycle as compared to the metal and the wood, which are the conventional material to make the different articles. But recycling is also having its limitations, because a virgin polymer, when it's recycled more than 2 to 3 times, it is losing its molecular weight because of the thermal stress. And that is why eventually we have to discard the plastics. That is why we are looking for the alternative polymers or alternative materials which can substitute the plastics in certain areas, not at the plastic as a whole, but particularly the plastic for the packaging applications or the particularly the single-use applications. Now, if we have a overall look for the bioplastics, we can have the plastic which is conventional plastic like the PET, polyolefins, and the other polymers. And these are the polymers which are the non-degradable in nature. And then comes the another kind of polymers, where these are the polymers which are having their raw materials coming from the nature. Also, these are the non-biodegradable but the bio-based polymers. So eventually, these polymers are non-degradable in nature, but because they are raw materials coming from the nature, that is why it is also coming in the category of the bioplastics. And then another category where the polymers like the PBAT and PCL are there. So these polymers whose raw materials or are coming from the fossil oil, but they are because of their chemical structure is like that, because they are degradable in nature. So these are the polymers, which is another class of the bioplastics. And then the third class is the polymers, where the both raw materials are coming from the natural resources and the polymer itself having the biodegradable nature. So the overall thing is that the bio-based does not necessarily mean the biodegradable, and the biodegradable does not necessarily mean the bio-based. Coming to the next slide, and we have the global production, because it is showing that the both two polymers, where the bio-based polymer which is non-biodegradable in nature, and another is the biodegradable. So the bio-based plastics are roughly the 42% of the overall bioplastics, and the 58% is the polymers which are having the biodegradable nature. And if you look particularly for the biodegradable polymers, the PLA is the commercially highest produced material, and then comes the PBAT, and then the starch-based blends are there, and which are obtained from the natural resources. And sector-wise, if we look at where the bioplastic is mainly used, and it is coming, the major sector is the packaging sector, where the both rigid and flexible packaging is coming, and then comes the consumer goods, textiles, agriculture, and horticulture. So the packaging is a major area where the bioplastic is being used these days. Now, in terms of the processing industry, if we talk about particularly for Indian scenario, because currently no big companies there who is making these biodegradable polymers like the PBAT, polybutylene succinate, or the PLA. So mostly the processor in the country, they are importing this material and converting into the suitable blends or the composites. And so generally because they are adding fillers and additive in it, they are adding additives, range of additives as per the application, like the antioxidants, UV and light stabilizer, plasticizer, lubricant, slip agent, and anti-blocking agent. And in terms of fillers, they are adding the calcium carbonate, talc, silica, and the starch and cellulose kind of natural base fillers. And fillers is also very important while they are making the extrusion process and making the blends of these polymers, because these polymers are having the higher cost as compared to the conventional polymers, and fillers can be a very good thing for the cost reduction also, and as a processing rate. And we look at the various kinds of processes where the converters can convert into the final materials or the final products. And the one is the blown film process, by which they are converting the carry bags, garbage bags, mulch films, and the packaging bags are the major area where the mainly the converters are working in the processing industry. And then comes the extrusion process. In extrusion process, they are converted to the net or the fish nets, and then injection molding is the process by which we are converting into the rigid packaging. 3D printing so far for the biodegradable polymers in very nascent stage, and then other processes are the thermoforming process and the thermoforming process, and these processes are used for making the cutlery items which are disposable in nature, and these are widely converted by the or the made by the consumer because they are in the very good demand in the market after the particularly the ban of the conventional plastics. Now, particularly for Indian market, the major polymers which are being used are the PLA, PBAT, polybutyl succinate, and somewhat PHA because it is also cost effective. It's not cost effective; it's very costly. But majorly the PBAT and PLA blends are majorly used for converting into the films, and those films are using for the packaging applications. And the major segments are the packaging, textiles, agriculture, and horticulture. And the key players in Indian market are the Evergreen, Ecolife, Plastobags, Earth Souls, Trugreen. And apart from these polymers which are biodegradable in nature, certain other products are also available in the market, like the oxo-degradable polymers, and they are adding the metal salts in it to make it more photodegradable. But these plastics are not biodegradable in nature because they just make the fragments of the plastics, and those plastics never get degraded in the natural environment. So these oxo-degradable plastics are also not considered in the criteria of the biodegradable plastics. But they are there. But these kind of plastics are there in the market, which is being sold in the name of the biodegradable polymers. Now, the packaging segment is the projected to be the dominant in the India's bioplastics industry, and this accounted nearly 60% of the overall market. And these bioplastics are commonly used for the bottle constructions, loose fills, cups, bowls, glass, flexible films, and other things. And the finished packaging products from the bioplastics are used in the packaging of the fresh foods, dry snacks, candy, bakery products, juice bottles, and the meat trays, as well as the coating for the drink cup and the drinking cup, and the films and the card stocks. Now, these are some of the applications which are emerging in the end use in the segment of the bioplastics in India. These are the metallized biaxial oriented PLA films for the food packaging. Agriculture mulch film is another segment. Then the bioplastic films for the sanitary napkins and diapers. Microbeads from the bio-based and the biodegradable polymers substitute the conventional polystyrene foams based styrofoams. Currently, there's some of the foam products of the biodegradable polymers are coming in the market, and also the shrink wraps. Then the baby products like the toys and teethers and baby feeding bottles and 3D printing. These are some of the segment which are now emerging in the bioplastics in India. Now, eventually, whatever the products are there, they should be the biodegradable nature. That is why the USP of these materials. But biodegradable is always a matter of the surrounding environment, because if you have one biodegradable materials, but the conditions conditions are different for the two different places, then the rate of degradation will be different because it depends upon the concentration of the microorganism, temperature, and humidity. So the rate of the biodegradation depends on the real life conditions in the composting plants, in the home compostable or the environment. That is why there is a need for some of the certification for the compostability. And currently, the industrial composting, there is a particular standard like the ASTM D64400, and these other standards are from the other countries which are being used for the industrial compostable for the industrial compostability, and where it is required that whatever the material is being tested should be able to convert its 90% of theoretical carbon into the carbon dioxide during the 180 days of the test period. So industrial composting generally having the temperature of the 58 degrees centigrade temperature, and the 6 month is the test time. Another category is the home compostability, where the temperature is the 28 degrees centigrade temperature and the time period is 12 months. And in even the fresh water or the soil or the marine environment, everywhere that the the carbon which is having in the theoretical carbon should be convert up to the 90% should convert into carbon dioxide and water in the different conditions. Particularly for India, CPET is the agency where the test, this ISO 17088 can be done, and here this is a similar, which is the ESTM standard 6400, and the 90% of this theoretical carbon dioxide should convert into the carbon should convert into carbon dioxide and water in 180 days. And currently in Indian scenario, carry bags which are made from the virgin plastics shall not be the more than 100 micron thickness and less than 100 micro thickness, and where the some certain plastic waste management rules, and these rules are not applicable for the compostable plastics, and which are complying the ISO 1700. And so and according to the Center Pollution Board, any converter or the processor which are making certain articles, they have to take the certificate before the marketing or the selling of these products. Now, if you look at the opportunities where there are the different drivers for the bioplastic market, first is the compostable plastics, because they are costly 3 to 5 times higher than the conventional plastics, and that can impede the market growth. And that is why the technological stabilization and the cost reduction is very important. And second thing is that because the demand is increasing from the various sectors, one of the reasons that the mandate and regulation from the governments, and also from the various social media platforms, people are getting more aware about the eco-friendly materials, and the companies are also becoming more focused on the sustainability of the final materials. That is why there is a higher demand is looking in the future, and particularly for the Indian point of view, and if we lead the more demand of the biodegradable polymers, and then the master batches, key ingredients, raw materials, and which are now being imported. In future, it is possible that the indigenously we can produce this material to meet the market gap in supply, because many times the converters are facing problem because they are not having the material also, and also the cost is very high. So it will have it will provide the opportunity for the Indian players to come into in this field and produce the various components of the biodegradable polymer or the biodegradable plastics indigenously. This is all from my side. Thank you very much. And I would like to acknowledge my mentor, Dr. D.K. Gupta, Senior Vice President, Reliance, and I would like to thank the ICPE for giving me opportunity to share the stage with the distinguished speakers. Thank you. Thank you very much.
Thank you, Sunil, giving such an overview of what is the biodegradability composting facility and what we do. With this, we come to the end of this first session with the speaker. Now we'll move on to the panel discussion session, and there will be more interaction. Even some of the questions which may have raised may be taken up at the end. So I may like to now hand over this panel discussion session to Mr. S.K. Ray to conduct the session and coordinate for the panel discussion, please. Mr. Ray, please.
Yeah, thank you, Professor Ghosh. I think we had a very, very interesting session so far. And I must admit that after this session, I am no wiser than what I was in past before the session started. My confusion still remains, and I think this is what is science is talking all about on something which is getting developed and evolved. I have few points to make. One is, of course, a house keeping point. Unfortunately, Professor Dubey had a flight to take, and the flight was late, and that actually clashed with this timing that we have for the panel discussion. So he had to sign off, and he has conveyed his regret for this. Nevertheless, he had made few points, but before that, just for the sake of continuity, I'll briefly mention all our other panelists. They have already been appropriately introduced by Professor Ghosh. So I'll only make a brief mention of the other two panelists that we have during this session. One is, of course, Professor Dubey, and then we have Mr. Jivraj Pillai. Mr. Dubey has sent few comments that he has on this particular topic, which I'll share it with you. But briefly, just to do that process in the way it is expected to be, just very brief introduction of both these two new panelists that have joined us. Let me take you through that. First of all, Professor Dubey is not here with us, but just to give a brief background of his, he did his BTech honors in civil engineering from IIT Kharagpur and PhD in environmental engineering science from University of Florida, USA. He is presently in the division of environmental engineering and management, Department of Civil Engineering at Indian IIT Kharagpur. He has over 20 years of research experience, teaching and training, and industrial outreach experience, and has co-authored more than 200 publications in this area. He has presented at several national, international conferences and has worked as environmental experts for UN agencies, World Bank, and agencies such as National Geographic Society USA. He has worked on integrated waste management projects in several countries, including US, Canada, New Zealand, Australia, China, and Nigeria, amongst others. Professor Dubey has offered courses and training programs in the subject areas of waste management, resource recovery, environmental risk assessment, circular economy, and sustainable engineering. Professor Dubey believes in practical applied research and has worked with several government agencies and industry trying to solve the problem using strong scientific fundamentals for long-term sustainable solutions. Recently, his team has developed carbon material from food and yard waste as part of resource recovery and waste to wealth, which can be used as fuel, adsorbent material, and also as energy storage carbon, which can be used in batteries. The technology has been tested in lab scale and a small pilot scale plant, which is his team is planning to take it to in the next level with a pilot plant soon. Wish we had him join us for this panel discussion. Unfortunately, he could not. So briefly, few of his thoughts he has left it with me, and I would like to share that with the attendees here. Okay. Okay, let me say that. Oops, too many. Okay, few of his points that he talks about. Plastic as a material is not a problem. Plastic waste is. We should work on improving the plastic waste management infrastructure. That is his point number one that he has left with us. Point number two, he mentions about, in my view, recyclable regular plastics should be collected properly and recycled. We do not need to focus too much on replacing the good recyclable regular plastic materials. There's a point number two he had for us to ponder out. Three, he talks about for SUP, we should focus on having 100% biodegradable plastics. Mixing different plastic material affects the composting process. The rate of reaction of compost process will be different. Mixing good waste, readily degradable organic waste with bioplastic does not work. That's what he believes. If we mix bioplastics with traditional good quality recyclable plastics, we are creating problem for plastic recycling industry. Then he says, I'm sorry, I have to board the plane now. So that was his comments before he had to leave this panel. So anyway, we'll catch up with him in some other occasion. So what we'll try to do is that I'll also briefly introduce Mr. Jibras Pillai from UFlex. Mr. Pillai is a mechanical engineer and a postgraduate in business administration. He has over 34 years of experience in packaging, which covers the entire spectrum of packaging technology. On the sustainability front, he has been working for past 10 years on addressing the issue of the damage caused to the environment by plastic litter. By implementing various measures, including recycling of multi-layer plastics, he has been actively involved in development of viable biodegradable option for the packaging industry, including that under litter conditions and monopolymer based barrier and non-barrier laminate structures that he has developed. His contribution in implementing the energy curing technology in flexible packaging has resulted in a substantial reduction in carbon footprint. He has presented papers on sustainability, plastic packaging and environment, moving towards a circular economy, application of E-beam technology for curing, and monopolymer-based flexible packaging material, to name a few. He is one of the co-founder of PPRDC, which exclusively works on sustainable solutions to plastic waste issue. He has won awards from AIMCAL, FPA, and DuPont for sustainability development. Here is a person who has huge amount of experience, practical experience in looking at plastic packaging and how the concept of biodegradability could be introduced here. And I have noticed him very passionately pursuing this. So what we would do, we would probably request Mr. Pillai to say a few words. Then I would try to pick up few questions which have come in the QA box for our panelists to respond to some of those questions. And at the end, maybe we can also ask some questions, take some more questions from the audience and proceed accordingly. So may I request Mr. Pillai to say a few words, maybe take 5 minutes or so to articulate his thought on this biodegradable compostable plastics. Over to you, Mr. Pillai, please.
Thank you, Mr. Ray. I hope I'm audible enough.
You are audible, yes.
First of all, I would like to thank ICPE for the opportunity provided to participate in the discussion with such power-packed speakers and panelists. Basically, I'm a process specialist. I'm not an academician or not done very research work in biodegradability. But as a process specialist, we always try and find a mid path. So we don't entirely depend on the material science for solution, but we try and find a process solution. We at UFlex, along with its group companies, produce and supply about 20,000 metric tons of flexible packaging material per month, largely MLP, out of the total 125,000 metric ton consumed per month in our country, which essentially is 17% of the market share. So in a way, I can be the voice of the converting industry in this panel discussion. I will restrict my discussion on MLP, which constitute about 70% of the packaging consumption and waste. I gather from all the presentations so far that there is no ready-made solution for biodegrading the MLP, which are primarily made, flexible packaging material primarily made out of fossil plastics. We heard and conclude that bioplastics certainly cannot be used in MLP. Hence, do not wish to repeat the reasons why bioplastics cannot be used in MLP. My take on this is the following. We discussed theory X. Theory X says MLP cannot be biodegraded. It is fossil plastics and very difficult to biodegrade. We also discussed theory Y, why bioplastics cannot be used in MLP because of the functional limitations and many other issues which make use of bioplastics in MLP very difficult. Why can't we discuss theory Z? What I mean to discuss here is that can we find a solution where we can be in the middle path? Can we make the contradictory requirement complement each other? So the functional requirement of the hydrophobicity, which is very important for the active service life of the packaging to keep the barrier and the functional properties alive. And once the active life is over, can we make it hydrophilic? We all know that once a level of hydrophilicity is achieved, it is possible to biodegrade the fossil plastics. So why don't we work in a direction where by infusion of certain enzymes, certain catalysts, certain assistive catalysts, can we create a biodegradability after the service life is over? Could a recipe in combination with bioplastics, enzymes, and oxidative additives be made so that it behaves in a certain fashion till the service life is active, and it behaves differently or in the completely opposite manner when the service life is over? You know, can we redefine biodegradability in terms of its time span? Why are we restricting ourselves to 6 months? If the plastic is not biodegrading in 100 years, can we have a 10-year lifespan, 5-year lifespan? Can we slow down the biodegradability process by adding something very minutely possible and biodegrade it in 5, 7, 10 years? You must all be surprised to know that the foundation of Taj Mahal is on a wooden plank, and wood is considered to be biodegrading. So if this wooden plank is not biodegraded for 300 years, why are we insisting on something which will biodegrade in 6 months? Today, we have to beat the first benchmark of 100 years or 200 years or 300 years. Let us begin with 1/10 reduction. So slowing down the biodegradability process will help us discover and invent material which would create some biodegradability or hydrophilicity after the service life is over. This is my take on this. Can we also redefine the end product after biodegradability? Today we are too much worried about microplastics. Can we have a bio erosion instead of cleavaging? See, everything what we talk about is cleavaging the material, converting into microplastics. Can we have a bio erosion? Say, for example, if I'm using 100 micron film, can I make it 90 micron after 6 months? Can I make it 80 microns after 2 years? Can I make it 10 microns after 10 years? This way, you are not only redefining the biodegradability process, bioerosion will help you achieve your ultimate goal of biodegradability. So these are some of the takes, as I always say, if material science is not able to provide a ready-made solution today, why don't we work on the process and try and establish something in a middle path? As an optimist, I don't want the audience today to go back home, oh, nothing is possible, let us live with the MLP and remain in the fear, and all those numbers which have been projected is causing fear that what will happen to our children and grandchildren in 2050, 700 million tons of plastic, this, that, and all. So instead of relying too much on materials, and material science is always important, I'm not against that, but let us also be optimistic and try and develop a solution which is which I call it as theory Z.
Yeah, thank you, Mr. Pillai. I think Z is the last alphabet, but not the last in this session, right? We can still have that option of looking at Z, theory Z. Very good, very well articulated, Mr. Pillai. There are a few questions. Possibly, I'll pick it up from the chat QA box and request the panelist or the speaker to respond to. And no wonder the first one I got is for Dr. Shivram, and it has come from one of our participants. Sir, is it possible to make biodegradable polymer at polymer manufacturing stage or PE? I think we did mention that, but maybe Professor Dr. Shivram may like to respond to that. Is that okay, Prof? I don't see Professor Shivram. Maybe he may have stepped out. A possibility. So we go to the next question. Or we have a question from one of our participants. What are the gaps that India needs to bridge in terms of bringing in plastic packaging solutions for circular economy point of view. No better person than Mr. Pillai to respond to this. You just talked about this, right? Mr. Pillai, any view on this?
Yeah, could you please repeat this question, Mr. Reyes?
Yeah, what are the gaps that India needs to bridge in terms of bringing in packaging solutions for circular economy point of view?
So it's very important to note that, in order to remain in circularity, the most preferred option will be recycling. So there is a technology available for recycling all types of plastics, including MLB, and convert it into some downcycling form where the material can remain in circularity. Biodegradability should be the devil's alternative. If you are not able to pick up, if you are not able to recycle, then only it should be allowed to biodegrade. Because many countries, in the best country which I have seen is Sweden, which collects only 70% of the littered plastics. So India is like 80% littered plastic. So the biodegradability is a good option today, since we are not able to collect. But as we build up the infrastructure of source collection, we must focus more and more on recycling. The plastic is a wonderful molecule. It can be recycled thousands of times. All we need to do is to find an application for the recycled material. So in order to remain in circularity, today the biggest gap is the infrastructure of recycling in India. We require, in a ballpark, back of the hand calculation, we need something like 1,500 recycling plants to address all the 125,000 metric tons of MLP produced and consumed in this country. We have against that only 20 of them. So this is perhaps the biggest gap. Yes, biodegradability will find a solution. It is going to take some time. There are scientists working on it, and soon we will find some solution. But till that time, this is a lower hanging fruit. We must install infrastructure of recycling. Thank you, sir.
Thank you, Mr. Pillai. The next question we have from the audience is this is in reference to recyclability of low surface energy polyolefins, polypropylene, polyethylene, etc. Can we consider using tile layer adhesives stroke grafting for work or copolymerization as a promising prospect, especially for the packaging industry globally? This is a tough question. I have to really understand who would be the best person to respond. Professor Ramaninaran, would you like to respond to that?
Yeah, I saw that question and I wasn't very clear on where that was driven to. The use of tile layers and to build better adhesion and all is now facing increasing scrutiny from a recycling perspective, and the new designs go for monolayer films, right? Because if you have a mixture of resins, then you're not going to be able to recycle it chemically or mechanically, and so that's where the issue comes up. And so the design has to be that the tile layer should be the same as the polymer, the two polymers you have. And when you have a multiple polymer systems, then recycling is off the window. Of course, people will talk about compatibilization and all that, but in general, monolayer film or monolithic material is the best way to go. I'm not sure if that answers the question, but I wasn't sure what that question was alluding to.
Yeah, thank you, Prof. The next question that we have from the audience, biodegradable plastics have not grown over multiple decades, and we are also hearing many associated challenges. And the question is, then why are we promoting them? Would anyone like to respond? Professor Bhimal Khatir, would you like to respond to that? You are muted, Prof.
Yeah, I think it is really a very pertinent question that though we are advocating since decades, but still the ground reality says that we are still at the initial level as far as the country is concerned. The fact that we do not have any ecosystem, I mean to say so far, any commercial unit, though the interest has been taken up, and I can see, I may not quote, but I can tell to the participant that the activities are going on at bringing it to the semi-pilot and commercial scale. And certainly these new classes, because these kind of materials and technology has to be evolved depending on what is their requirement. So certainly things are, I mean to say, we are working, and others are also working on the similar line. So hopefully very soon we would like to have it some indigenous establishment for these kind of plastics. Important, a lot has been discussed on biodegradable plastic and conventional plastic. Yeah, absolutely right. Even though if you consider, if you take it all, whatever the biodegradable plastic is available in the world, if you are really going to consider all these positive, then still we do not have adequate, I mean to say, commercial, the quantity what we really require. So as Mr. Pillai has mentioned that we have to go with the conventional plastic. Also, in order to like recycling, we have to adopt a recycling also, as well as, but at the same time, we have to find out where we can cut. I mean to say which particular segment and portfolio which is really required in order to bring it to the to solve some of the problems. So that way I can say, and though it is very, very important questions that we have to have our indigenous capability on different class of biodegradable plastics. Some of the organization working on it, and certainly we will be having our footprint on that in this regard.
Yeah, thank you, Professor Khatir. Appreciate. We have a couple of more questions. What is the percentage of compostable plastics in total plastic used today, and how much is it projected by? I think we had a slide on that broadly. So I think we'll move on to the next question that I see in the QA box. Performance of some of the banned products in plastic waste management rule that we have list cannot be met by compostable polymers. In such case, what will experts recommend to the plastic waste management rule in our country? Maybe I can take some help from Dr. Balakrishnan to respond to this question from our audience. Dr. Balakrishnan, would you be?
Yes.
Please go ahead.
Sure. Yeah. Yes. As we all know, compostable or bioplastics cannot meet the performance requirement of all applications. And kind of stepping on to the earlier point that Dr. Khatir had also mentioned, why is there so much discussion on compostable plastics or biodegradability is also because we are trying to a highly commoditized industry like conventional plastics with still a very specialized industry of bioplastics. I mean, there is just no comparison at all. Plastics have been around for a really long time. The bioplastics are still pretty nascent compared to that. Now, coming to this particular question, I think not all applications, and there are certain areas like barrier packaging or single-use requirements of certain performance applications where compostable plastics cannot meet. But if we look at some of the banned items today, at least that is proposed, whether it's a earbud or a lollipop stick or cutleries or bags or single-use carrier bags or even products like food serviceware, most materials can be replaced with compostable plastics. There are alternates, and in certain areas where compostable plastics cannot be used, we could use products which are in combination with hybrid products like paper, which is a great value add Because, for example, most compostable plastics, I'll just take one example here. Most compostable plastics have challenges in heat resistance. I mean, PLA as a polymer itself is not very heat resistant. But when you coat it with paper or bagasse or another product, the heat resistance property of that hybrid product is much higher as compared to the original polymer itself. So this is one approach by which we could create hybrid products with compostables, which can help meet some of the application requirements.
Thank you, Dr. Balakrishnan. I do see a lot of many questions in the question box. Some of them Professor Ramaninaran is probably trying to respond to. Thank you very much, Prof. That would be really helpful, because in the process we can save few minutes. We are already running short of time. There is a question, just one, maybe one more questions we'll take before we sign off for the day. This is
Mr. Ray, I would like to say something.
Please,
so
please.
that there was a discussion, like Sundar has already mentioned. I'm fully agree with the Dr. Sundar that there are many applications where the compostable plastic performance are going hand to hand, and those segment, even though it has been targeted, even especially for a single-use plastic, is going to be, even though we could not able to cater the need of to addressing those segment, even though we would like to have a million-ton industry. So I think we have to figure it out what we can, where these kind of compostable resin can deliver, and at least we have to make the room. There are challenges, but we have to go ahead and take that particular segment for further commercialization. Thanks, sir. I just want to say.
Thank you, Professor. Thank you, Professor Khatir. There are, as I said, there are a lot more questions here. Possibly I'll pick up just two of them. One looks like to me more as a comment. The emphasis is more on biodegradable plastics, but is enough research being done in the field of recycling technology? Otherwise, how do we talk about circular economy for plastics life cycle? Very, very pertinent questions. As I said, possibly this is an observation and less of a question that that is there in this chat, in this QA box. Thank you very much for that comment, for sure. The last one, possibly we'll take it up before we close, because we are already, as I said, running short of time. This is addressed to Dr. Balakrishnan. Wouldn't bioplastic affect the recycling chain that is well established for conventional plastics? So why push for such material in India until composting facilities are available and citizens learn how to segregate? Dr. Balakrishnan, this is for you.
Yeah, sir, can you, I just lost the signal in between. Can you please just repeat that question? Sorry about that. Yeah.
No issue. I'll repeat that. The question is, wouldn't bioplastics affect the recycling chain that is well established for conventional plastics? If so, why push for such material in India until composting facilities are available and citizens learn how to segregate? So this is the question for you.
Okay. Beautiful question. So first thing is, what we'll have to understand is, if you look at the recycling channel, while everyone talks about recycling, statistics say that hardly the recycling rates of this very short lifespan, food contaminated materials, plastics, is extremely low. Now, you never talk about anyone saying that a PET bottle is on the road, or we look at recycling of PET, because that channel is extremely well established and there is value in collection of those kind of bottles. So the first point is the recycling rates of single-use plastics, and especially post-consumer waste plastics, is low because it is difficult, and this is not only seen here, it's seen across the board. So this is one. Second is, that right now compostable plastics are very less. I mean, they are, I would say in a country like India, it is even less than 0.1% of the total plastics. When you look at a recycled plastic stream today, even leave out the compostable plastics, there is no purified stream. No one is recycling only LDPE or HDPE or polypropylene or PET separately. So even your existing recycled plastic stream is a cross-contaminated stream. It is going to have polystyrene and polypropylene and polyethylene and maybe mixed with a few PET and maybe mixed with some of these inorganics. And compostable plastics is not going to make a huge difference in this because it's such a small portion. It's also a thermoplastic if you look at it. If you heat it, it melts, it flows, it kind of goes into the system. But when you look at a PET bottle recycling stream, then adding materials like compostable plastics create challenges because now you are disturbing a very clean recycle stream like a PET bottle. So the way we would have to structure this is almost kind of dissect this problem into conventional plastic recycling or an organized recycling like PET. In terms of post-consumer waste, conventional plastic recycling, with a cross-contaminated stream, compostable plastics is not going to make a huge difference with the existing volumes. But then for materials like PET, definitely we would want PET as a polymer to go forward and not cross-contaminated with a compostable plastic. So that is why if you see even companies like NatureWorks who make PLA consciously took decisions to stay away from this whole bottle manufacturing because they felt that PET was a great material as far as some of those applications are concerned. So again, coming back to the point that compostable plastics are specific and have to be specifically construed for certain applications.
Thank you. Thank you, Dr. Balakrishnan. I also do see Professor Ramaninaran possibly has also responded to your QA, your question. Maybe you can have a look at that as well. For the sake of, I think we have overrun the time as it is, and my apology on behalf of the organizers for this time overrun. We will close it now, and I would really like to thank all our speakers who have taken their valuable time and shared their insight with us in this webinar. So tons of thanks to all of them, and in particular Professor Dr. Shivram, Professor Ramaninaran, and my other distinguished speakers. Many thanks from us, from the organizers. Thanks to Professor Mishra, Ashok Mishra, he has also joined us. Thank you, Prof, for joining us, and I really appreciate your taking time out and joining us on this. My personal apology that Dr. Dubey had to take the flight and he couldn't spend much time with us. Thanks to IIT Alumni Center, Bangalore, and of course our friends from Polymer Processing Academy. Just a thought, Professor Mishra, would you like to say a few words before we close off? So before we all sign off, and of course, to all my participants who have joined us.
Okay. First of all, I really enjoyed the session. I personally don't work in the area of biodegradable polymers, but what I heard today was very exciting. But I think the challenges remain how to deal with the systems as we move forward. Lots of points were raised. One of the thoughts which I've always had, although I'm not a chemist, is that when nature can make biodegradable polymers like cotton and silk and all that, why can't man do it? So I think we have to move toward that realm. There was a scientist at Monsanto many years ago by the name of Ganesh Kishore, and he was working with as a biologist. He was working with plants, grow plants that would make things like, which are equivalent to polyethylene. I don't know whatever happened to it. That was about 2 decades ago. So if we can do that as we move forward, I think that would be the ultimate goal. But thank you to all the speakers. I'm so glad that we joined hands, ICPE and PPA, and of course, Alumni Center. I happen to be the president there also, but I didn't want to step in that role as what the show come and does a brilliant job. What he pointed out was a challenge. We talk about all these things, but yet when something comes from Amazon, we never write to Amazon and say, why are you doing this? You know, some of the packaging of Amazon, I took Amazon as an example, Amazon, Flipkart and all that, is absolutely redundant. It need not be packaged so extensively as they do. And same thing applies to their cardboard. I'm throwing more cardboard than I've ever before in my life through all these packaging. So it's a packaging problem. Of course, a polymer problem, but a packaging problem in general. So thank you so much for giving me the opportunity, Swapan. You did a brilliant job, and Anup conducting the session. I think maybe 6 odd months from now, we should rethink it and see what's going on in this area. We need to be at it on a mission mode rather than once in a while mode, you know, to make that difference for lives of people, for sustainability, as Shivram said. So thank you so much, and greetings from Amherst, where I'm sitting right now, University of Massachusetts, which is the hub of polymer, and they are talking about upcycling, and I will share those thoughts with you later sometime in the group. Okay.
Thank you, Professor Mishra. Thank you. Appreciate. And to all our guests joining from US, have a good day. And to all our friends from India, good evening and take care. And we'll be in touch once again. And do join us tomorrow as well. All of you who are there. Tomorrow we have this session starting at 4 o'clock. So do join us for that session as well in the Industry Academia interactive session. Thanks everybody, and say
I will intervene here. Those of you who joined today, please ensure that tomorrow's login is separate, which Professor Sursati Bose has shared with you. So just because you logged in today, it's not automatic for tomorrow. So you have to log in separately tomorrow, and look forward to seeing you.
Yeah, okay. The link is in the chat, sir.
Okay. Yeah. Thank you, everyone. Thank you. Thank you very much. Thank you. Take care.
Thank you. Bye-bye.
Bye.